B.R. Ambedkar Institute of Technology, Jalandhar. Welcome you all to the inauguration ceremony of GIAN course on modern composite materials, manufacturing and applications, new generation. Module in the dynamic realm of advanced composites. It explores the unique properties of composite materials. A central focus of the module is on the advanced manufacturing techniques that have revolutionized the production of composites. Methods like automated fiber placements, resin infusion, and additive manufacturing not only enhance efficiency but also enable complex geometries and structures which are previously unattainable with traditional materials. By equipping participants with a deep understanding of composite materials and their applications, the module aims to inspire innovation in engineering, design, optimization. Encourages participants to explore new possibilities in composite technology, preparing them to meet current challenges and seize future opportunities in diverse industries. We are honored to have with us distinguished dignitaries who have great with their presence. It is with honor event ceremonial lamp. I invite all dignitaries to light the lamp blessings of Ma Saraswati. Thank you, dignitaries. As we begin, I would like to extend my heartfelt gratitude to our esteemed director, Professor Binod Kumar Konajia, for his unwavering support and visionary leadership, who due to prior commitment is unable to join us today. indeed my privilege to introduce and warmly welcome our distinguished guest of honor and speaker for today, Professor Chongdu Cho. To honor our esteemed speaker and guest of honor, I would like to invite course coordinators Professor Anis Sachdeva and Dr. Narendra Kumar to kindly felicitate Professor Chongdu Cho. Chongdu Cho is Professor of Mechanical Engineering at Inha University, South Korea. His career covers more than 30 years of research. His laboratory monitors the most recent research trends in industrial technologies. We are honored to have him with us today to share his insight and experiences, which I am sure will greatly enrich our understanding and perspective. On behalf of organizing committee, I extend a heartfelt welcome to you, sir. It is truly a privilege to have you here with us. Ladies and gentlemen, please join me in giving a warm round of applause to welcome Professor Chongdu Cho. Now I would request Professor Arvind Bhardwaj and Head of the Department Rakesh Kumar to honor our guest of honor and Registrar of the Institute, Professor Ajay Bansal. Thank you, sir. To honor our distinguished guest, Professor Mamta Khosla, Dean, Industry and International Affairs of Institute, I invite Dr. Narendra Kumar to kindly come forward and honor ma'am. Now, I would like to invite Dr. Vikas Kumar and Dr. Aviral Mishra to kindly come forward and facilitate our Head of the Department, Rakesh Kumar. Finally, let us all come together to show our collective gratitude to all our honored guests for their significant presence in giving them a resounding round of applause. Thank you to all our esteemed dignitaries for gracing this occasion and making it truly special with your presence. As we move forward, I would like to invite our Head of the Department, Dr. Rakesh Sharma, to kindly brief about the department.
Our distinguished guests of honors, Professor Chongdu Cho, Professor Inha University, Seoul, Professor Dr. Ajay Bansal, Institute Registrar and Professor Chemical Engineering Department, Professor Mamta Khosla, Dean International Affairs and Professor ECE Department, Professor Arvind Bhardwaj, Professor of IPE Department, my colleagues from NIT Jalandhar and dear participants. On behalf of the Industrial and Production Engineering Department, I extend the heartiest welcome to all of you. This course is an outcome of the visionary zeal of our institute team, led by Director Professor Binod Kumar Kanojia, who has always stressed on expanding the frontiers of knowledge through exchange of ideas. He has stimulated NIT Jalandhar to host a number of short-term courses, faculty development programs, workshops, and conferences in last 3 years. Realizing the vision of our worthy director, Professor Anis Sachdeva, and Dr. Narendra Kumar has designed the present course as a step in this direction. This course of 6 days duration, December 11 to 16, 2024, is sponsored under the Ministry of Education scheme, Global Initiative on Academic Network, GIAN, entitled as Modern Composite Materials, Manufacturing and Applications, New Generations. Course coordinators will put more light on the importance, relevance, and contents of this course. On behalf of the Department of Industrial and Production Engineering and the organizing team, I extend warm welcome to Professor Chongdu Cho from Mechanical Engineering Department of Inha University, Seoul, South Korea. As an esteemed authority of this field, he will be the instructor of the course and enrich the participants with his in-depth knowledge and wide experience. His detailed credentials will be apprised by the course coordinator. Now I would like to introduce you to the Department of Industrial and Production Engineering. The department has been offering undergraduate program BTech in Industrial and Production Engineering since 1989. Postgraduate program MTech in Industrial Engineering and Data Analytics. We have staff strength of 25 members, including 17 faculty members. Presently, about 50 research scholars are also registered in the department for pursuing PhD in various areas of industrial and production engineering. The department has established 9 state-of-the-art labs for its UG and PG students and also has 2 research labs. The autonomy of the institute is a privilege to the department in terms of flexibility to modify and revise course syllabi at different time intervals to cater contemporary needs of the industry. Adequate inputs of practical training, industrial tours, case studies and project work, and computer applications are given to support our core theory courses. For this course, we have a group of 45 participants, including 30 from different states of India, around 15 of our own faculty members and research scholars from various departments have also shown interest in attending this course. I hope and wish they will certainly gain insights on what we have defined as objectives of this short-term course. With this vision, I once again welcome all the participants and wish them all the best for a fruitful learning experience from this course. I also wish all the best to Professor Anish Sachdeva and Dr. Narendra Kumar, coordinators of the course, for organizing it to the satisfaction of all the stakeholders. Thank you very much.
Thank you so much, sir, for giving the brief introduction of the course and the department. Now I would like to invite course coordinator Professor Anish Sachdeva to kindly brief us about the course.
A very good morning to all of you. Resource person of the program, Professor Chongdu Cho, Registrar, Professor Ajay Bansal, Dean, Industry and International Affairs, Professor Mamta Khosla, Professor Arvind Bardwaj, Head of the Department, Dr. Rakesh Sharma, Coordinator of the program, Dr. Narendra Kumar, my dear colleagues and dear participants. It gives me immense pleasure to welcome you all to the inaugural session of GIAN program on modern composite materials, manufacturing and applications in the new generation. This program has been meticulously designed to explore the advancements in the composite materials and their transformative role in modern engineering and manufacturing processes. You know that the composite materials with their remarkable versatility and adaptability have become a driving force behind progress in numerous industries. These materials are revolutionizing industries globally due to their exceptional properties such as lightweight construction, high strength, and durability. So whether in aerospace, automotive, civil infrastructure, renewable energy, biomedical fields, or sports and leisure equipments, these materials remain at the cutting edge of technological advancements. Their applications are essential for fostering a sustainable and technologically advanced. So this program will feature insightful sessions on the types of composite materials, their properties, and innovative applications across various fields. It will also cover cutting-edge manufacturing techniques for the composites, emerging trends, future directions, and the sustainability and recycling of composite materials. So these topics have been carefully chosen in discussion with Professor Chongdu to address the current industrial demands as well as societal changes, making them highly relevant in today's context. I would like to extend my heartfelt gratitude to our esteemed key resource person, Professor Chongdu, from Inha University, South Korea. We are deeply honored that he has graciously taken the time to share his vast experience in this field with us. So, Professor Chongdu Cho has an outstanding career spanning over 30 years in research and teaching. During this time, he has worked with some of the most reputed institutions, including KAIST, Republic of Korea, from 1983 to 85, a research center in the Hyundai Group, Korea, from 1985 to 1988, the University of Michigan from 1988 to 1991, and Inha University, where he has been serving since 1992. His laboratory is actively involved in studying the latest trends in industrial technologies. He has guided around 150 researchers, which include masters and doctoral students who are working in the various technical areas. Professor Chongdu's lab has published more than around 400 papers in the reputed journals and conference proceedings. His excellent research work has been recognized with several awards from the Ministry of Commerce of the Korean government, as well as from leading industries and academic societies like KSME and KSAE. His research work covers a wide range of fields, including mechanics, automotive engineering, robotics, and biomedical devices. Many of his projects involve combining advanced technologies to create new opportunities and make a strong impact. Apart from the research work, Professor Chongdu is also serving as a chief editor, editorial board member, and reviewer for many reputed journals. He has authored more than 250 research papers, 120 conference papers, and 3 book chapters, and with an impressive 3,258 citations to his work. So I am sure that his present and insights will undoubtedly inspire participants and open new avenues for research and application in these cutting-edge areas. I encourage all the participants to not only absorb the knowledge shared by our distinguished resource person, but also to explore the opportunities for collaborative work with him. I take this opportunity to thank our Honorable Director, Professor Kanojia, who could not join the function because of his preoccupation. He is also having the charge of Director NIT Srinagar, and he is there. He has always been a constant source of encouragement and support for hosting such impactful academic initiatives. We are thankful to the Registrar Professor Ajay Bansal and local GIAN Coordinator Professor Srivastava for their wholehearted support in making this program possible. We also thank all the participants who have joined from all over the country to attend this program. I am confident that this program will equip you with the knowledge and skill needed to meet the challenges of the evolving world of materials and manufacturing. Thank you. Wish you all the best.
Thank you so much, sir. It is now my honor to invite our esteemed guest of honor, Professor Ajay Bansal, Registrar of the Institute, to share a few words with us.
Invited expert speaker for the program, Professor Chongdu Cho from Korea. Head of the department, Professor Rakesh Kumarji. Coordinators of the program, Professor Anish Sachdevaji, Dr. Narinder Kumar, Professor Arvind Bhardavji from the department, Madam Professor Mamta Khosla, Dean International Affairs and Industry. It's indeed a pleasure to be part of this inaugural ceremony of this GIAN program organized by the department. I would like to a little bit talk about GIAN program, which is an initiative of Government of India, where it was envisaged that we should invite a speaker from some outside world having deep knowledge in a particular subject and invite him in person to the institute so that we can utilize his full potential and have a meaningful interaction with him for a longer period than usual lectures. So these 5-day, 6-day program, in fact, if you see, I'm sure that your classroom teachings or classroom lectures are not so engaged, and a leisure time, sufficient leisure time is given in between. And the motive of that is solely to interact with the expert available beyond the classroom teachings. Classroom teaching is one part where you get the basics of the program, basics need of the composite materials, applications, and new possibilities in that area. But every individual may have its own need, own thinking process, doing research in that area. And at one point or other point of time, you might be thinking that there should be someone with whom we can exchange our knowledge, or we can have a discussion on the point. And such program, especially these GIAN programs, provide ample opportunities to have interaction beyond the classrooms. Further, discussions amongst yourself is also key to the success of the subject, if I call. You can discuss amongst yourself, you can discuss with the course coordinators, because if you discuss with the course coordinators, they can plan future courses in a better way. So whatever lacunas, whatever the deficiencies are there, they can be overcome in the future courses, but I am sure that there will be lot many things to be taken away from this course. So I would also like to compliment the department for a couple of things. Normally such courses, we have a better venue as far as institute is concerned. We do most of the things in the video conference hall of the institute, but they chose this department venue, and I'm really very happy that they did at their own level in the department. There are things that whatever the facility we have in the department, if we start using it in a proper way, they get better and better day by day when we have more such programs organized in the department. Whole department has a cohesiveness together. They can see, even those who are not part of the course, when they see that our department is organizing this program within the department, they also come across and join hands, and the department grows further. So these few things are there, and the department always takes a lead in organizing such programs. I also been part as a professor in chemical engineering. In fact, this subject is very close to my heart as well, but due to my occupations, I'm afraid that I'll not be able to attend this program. But I wish that all of you make full use of the program, use to the fullest capacity the availability of Professor Chongdu Cho, who has spared his time from his busy schedule over Seoul and has come all the way. And it's not a very pleasant time in India these days, because we have very inclement weather, and winter is very severe these days onwards. So I wish that season is, I would say, cold, but you will feel the warmth of the course, and you will take away lot many things from this course. With these first, I would like to congratulate the department for organizing this wonderful course, and wish that 6 days will be meaningful and it will be a great success. Wish you all the best. Thank you very much.
Thank you so much, sir. As we near the conclusion of this memorable event, it is time to express our gratitude to everyone who made this occasion a grand success. To deliver the vote of thanks, I would like to invite Dr. Narendra Kumar to come forward and extend heartfelt appreciation to all those who contributed to this program. Before having a vote of thanks, I would like to invite our guest of honor and speaker of the day, Professor Chongdu Cho, to come on the stage and share his views.
Thank you for the generous introduction about me. I have not expected I am asked to give some sentences here, except my lecture. Yeah, I'm great honored to be invited to this program, and I have prepared the 13 modules of slides for the stay in this university, and I think most of my thinking can be encountered through my lecturing. So what I wanted to shortly talk here. Actually, my first year 1961 in South Korea, and at my elementary school days, as you see, the South Korean economy was not so great. It's very poor. So since then, the South Korean economy greatly developed, as you see these days. But that means for the last 40 years, that means since my PhD finished, the South Korea industrial progress was enormously huge. So that means I observed and I lived in that society, and I experienced much progress in industry, and especially in the field of mechanical engineering. So through those kind of progress, I think the material and processing and the application is most important in making great role in global market. So I want to share my experience about those kind of progress I experienced in South Korea at my short series of lectures together with you. If you give me many questions, then I can say something what I experienced through my very rapid development experience days. Okay. Thank you very much. I wish to enjoy together with you my lecture. Thank you.
Thank you so much, sir. Now I would like to invite Dr. Narendra Kumar for vote of thanks.
Thank you, ma'am. Okay, so good morning, everyone. Dignitary on the dais participants. So as we near the conclusion of this momentous event, it is my privilege to extend a heartfelt vote of thanks on behalf of the Industrial and Production Engineering Department of Dr. B.R. Ambedkar National Institute of NIT Technology Jalandhar. First and foremost, I would like to express my deep gratitude to our distinguished guest of honor and speaker, Professor Chongdu Cho, Professor Inha University, South Korea, for making the efforts to travel all the way to India from South Korea to share his valuable insights on the modern composite materials. And I extend my sincere thanks to our esteemed director, Professor Vinod Kumar Kanojia sir, whose unwavering support and leadership have always guided us. Though unable to join us today due to prior commitments, his encouragement has been pivotal in organizing this event. I am immensely grateful to our respected registrar, Professor Ajay Bansal sir, for his gracious presence and inspiring address today. Thank you, sir, for your continued support. My heartfelt appreciation goes to Professor Mamta Khosla, ma'am, Dean of Industry and International Affairs, for her valuable contribution. Your guidance and vision are truly appreciated. I would also like to thank the head of department, Dr. Rakesh Kumar sir, for his insightful overview and unwavering support throughout this event. Your leadership has been instrumental in making this program a success. A special thanks to course coordinator, Professor Anish Diva sir, for his meticulous planning and tireless effort in organizing this GIAN course. Without your dedication, this event would not have been possible. And also to local GIAN coordinator, Dr. N.K. Srivastav, for his guidance and support throughout the planning of this program. I am also grateful to Professor Arvind Bharadwaj sir and Dr. Vivek Dhimole. He is from Inha University, and he has supported me throughout this planning. and Dr. Rakesh Kumar, Dr. Vikas Kumar, Dr. Aviral Misra, Dr. Sita Soda ma'am, and other faculty members, and for assisting in facilitating today's event. So your contribution has been invaluable. Lastly, I would like to thank our participants, students, and the entire organizing committee for their cooperation and the support. Your active involvement, commitment have been the driving force behind this event success. So as we proceed with the technical sessions, let us carry forward the knowledge and inspiration gained here today. Thank you all for your presence and participations. May this course open new avenues for learning and collaboration. So wishing everyone a productive and enriching session ahead. Thank you.
Thank you so much, sir. Before starting the session, we will be having a tea break for 15 minutes. After that, we are going to start with the session. Thank you, dignitaries. Thank you. Attention all, after high tea, all of you are requested to assemble in front of the main director office for a group photograph.
hello, 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 hello. Hello, hello. Hello, hello, hello.
I have for 13 slide packs. Today I'll give you 2 of those. I guess you already have a series of lecture titles. And before starting this talk, I want to express my thanks to Dr. Vivek Timoli. He is now out in the corridor, I guess. Actually, he prepared all for this lecture series process. And because I do not know the exact requirement this kind of lecture series wanted to have, so I asked him to communicate with the staff in this university, and he decide the final titles and raw materials of each slide. So I just slightly modify his the prepared slide. So some kind of case, I think it is a little bit deviated from my main focus, but I think all material, slide materials are fine to give a lecture. So first one is lecture 1, series lecture 1. Is about introduction to composite materials and their significance in various industries. So before starting this lecture series, so I just talk a very brief academic background of mine about composite, so that it can be helpful for you understand when you raise your questions and what can be expect more the professional answer from mine. Okay? So about composite, so it's a long time ago. So National University, for my bachelor, my graduation thesis was about the design of a spiral heat exchanger. That means the thermal heat transfer, something like that is my one of the major background. And for master degree in KAIST, Korea Advanced Institute of Science and Technology, there my master degree thesis was about the theory and the modeling of interface crack. So that means durability issue of composite material or the semiconductor packaging issue. So it's one of my main research focus. And the University of Michigan at Ann Arbor, when I got a PhD, so my thesis was about mechanical behavior of ceramic matrix composites. At that time, my project sponsor was DuPont and Corning. So the high temperature use composite material.
This mic a little bit down. Voice is not audible.
Okay. Now it's okay?
Now it's
okay. So that means among many composite materials, the ceramic matrix composites mainly used for the high temperatures. So at elevated temperature, maybe the composite material mechanics and its processing is one of my main research focus. Right? And after that, during my sabbatical leave, I was in the Cornell University. At that time, I collaborated with the faculty about the mechanics of composites, so stress analysis, something like that. And after that, at the UCLA, their MEMS study was conducted, and that MEMS included the magnetostrictive materials. That means magnetostrictive material embedded composites can be used for intelligent switch composite, something like that. That is my main the titles so far about composites. So my main keyword can be said as mechanics and thermal stressing and composites. And to calculate and design composites, hand calculation is very minimal. It's not possible. That means for to use computational mechanics. So from my master degree days, I involved in programming to develop a finite element method. So far, in my laboratory, I programmed about 5 different the specialized finite element method program. Among 5, 2 of those are on the market these days in South Korea. So composite is very very vast concept. Actually, I can say all of material is composite. There is no pure material. Okay? But when we say a composite, that means artificially manufactured composite, rather than natural ones. So in that we can find the matrix terminology and reinforcement terminology. For reinforcement terminology, there's a particle or fiber, okay, fiber. Those terminologies can be found, right? So this case is automotive tire. So it is. So generally we say steel wire reinforced rubber, but actually that matrix itself, not pure rubber. In that matrix is can be classified as another composite as matrix rubber and with carbon particles. Okay? So it's very difficult the subject to calculate the development actually. And fiber orientation in fiber reinforced composite is very important. So you can see that this is a mono-directional, the fiber reinforced composite. And this is also mono-directionally reinforced one, but the difference between two is this one is continuous fiber, is used for reinforcement. This is discontinuous composite, discontinuous fiber is used to the reinforce the matrix. Right? And in this case, there is no preferred direction for reinforcement. It's randomly oriented. So in this case, usually we use chopped fibers. Chopped fiber, chopped fiber is used as a reinforcement. So this is a discontinuous and randomly oriented fiber. Each one is one ply. So each ply can be stacked to make an overall structure. This is the case, the stacking and bonded from each plies. Okay? So to satisfy some designated purpose of structure, we can intentionally make its stacking sequence differently. Okay? It can be calculated for having the desired stiffness in spatial directions. So then, as a result, the benefit is it's very balanced, and the in-plane stiffness can be easily obtained as desired. And there is also a sandwich panel. Is one of common composite materials, especially for bending structure purpose. In the case of moment should be borne to bear external bending load. So as you see, the middle surface in the case, middle surface of composite is not good for bearing moment, as you see. So to make it lighter, we make a very light and non the load bearing middle section is used. We say it is core. So honeycomb core is one of most the common shape for a low density core. And the benefit is we can make a very highly moment bearing panel, but with very small weight and large bending stiffness can be obtained. So composite material means it has generally, we can say, reinforcement added into matrix, then composite can be outcome. So definition of composite material can be said combining two or more distinct materials. So as a result, we wanted to create a material with properties superior to each component alone. Okay. So sometimes it feels like magic, because very tough material can be synthesized from very brittle two different ceramics. Okay. So, and as a component matrix, so many times it's called as binder. So the binder is especially for PMC case as a matrix binder. So binder means it's just to hold the reinforcement together. It is not rolling for the supporting any the excessive load. So most of the load will be supported by reinforcement only in this case. So example include the resin and the metal can be matrix. It's a resin case polymer matrix composite. It is matrix, depth matrix resin, and the metal matrix composite. As metal is matrix. So matrix can be any material. And the reinforcement also, its purpose is to provide strength and stiffness. So, example, the fiber, glass fiber or carbon fiber is very popular ones. And also ceramic particles can be used. Sometimes ceramic balls will be embedded into some aluminum alloy matrix or something like that. So the key idea to develop any special composite materials is to get high strength to weight ratio. That's a very basic characteristic of desired composite. And we wanted to have the long-term durability and flexibility in design. Okay? Because flexibility in design means because composite design, composite material design include is specially intended directional stiffness, not all direction. So a combination of different constituents in composite can provide composite material the unique property which are different from individual constituents. So we can find the much better the property as a result. And so although I said the composite consisted of reinforcement and matrix, but to evaluate its basic property of composite, there is one more characteristic must be focused. It is interface region. because between matrix and fiber, that zone is interface. Interface characteristic, most of time it holds the life of that material. That means durability will be seriously influenced by interface characteristic. So interface characteristic mostly will be influenced by manufacturing process. So good manufacturing means take good care of interface. Okay. So that is very important for final composite material quality. Then the manufacturing is very, very important. And this department is industrial and production engineering. Okay? So that means manufacturing is one of the main purpose of this department. I believe that the manufacturing process among three different major regions for composite materials is most important. The three regions means material itself and the computational mechanics from mechanical engineering part to design structure, something like that, between the manufacturing. So these three the specialties are very important. Among them, I can say, I wanted to say manufacturing is most important one. It decides the quality of marketing. Okay? So this is one of the typical cross-section of unidirectional composite materials. There, between the blue circle means a fiber or cross-section, and the gray background is matrix, in this case resin. And between resin and the fiber, there's interface, fiber matrix interface. This is very important. And also, so if there is too large matrix region, in the case, the composite quality will be degraded. So it must be cautioned. And reinforcement and layers. Layers, that means this is not a process in one the step. Usually it is a stacking, the manufacture through stacking, so each layer. So there are many, one layer, second layer, third layer, fourth layer. Okay? So each layer can make this kind of a hand layer. There are many different kinds of manufacturing techniques. Among them, this is one of the examples. So we make an open mold, and on it resin. Resin is prepared. On that, the fiber will be distributed, and resin, in the case, the many multiple layers can be prepared like this. Then after that, it is cured by using vacuum pack or top mold sometimes, and or hot pressing. There are many different kinds of manufacturing techniques. So this is for a very typical the manufacturing process for composite material. The resin transfer molding, RTM, so-called RTM, and winding molding, and the autoclave molding, and the compression molding. This is for typical processes for making composite materials. Each manufacturing method has pro and cons, of course. So for RTM case, pro is very efficient, and is very strong for pollution, against pollution, and the adaptability is very excellent. But during its processing characteristic, it can make much more air pockets. So high porosity can exist, and the controllability accordingly very low. And the winding process means its shape is limited to tubular type, and the productivity is very good because it can be automated. The reliability is very good, but cost is very high, and adaptability. For example, Inha University is owned by Korean Air. Okay. The Korean Air provide the flight service, but also it has manufacturing industry. So when I visited the Korean Air manufacturing plant, I can see the huge size of the winding machine. I heard it is 50 million US dollar. So for one machine, so it's very expensive. So we will discuss later. Today we will just see the very introductory level only, right? So autoclave or molding is it has a large. It can cure the large part. So the at that factory, when I visited there was one of the tail wing for airplane was autoclaved. So that means that autoclave size is 20 meter high. So it's very big. The autoclave can be properly working there. So, that means a large part can be cured properly, and very low porosity accordingly possible, and part of stability, property stability can be expected. But energy consumption is too high because it has a huge inner space to cure. That means heating and cooling, the energy consumption is too high. And that means cost is very high. And the compression molding case, the cost is very low, and low internal stress because it's very similar to the steel plate compression. So it's very traditional process, but infiltration effect is difficult. Preparation efficiency is very low. And so actually, composite material is not so. Sorry, composite material is not new material. Actually, it is one of very old materials. So it's going back to the ancient times, in Egyptian time, something like this. So we can find all of composite material, the characteristic structures from natural ones and ancient pottery, something like that. But we say in the 1960s, we got to know composite materials is very important to industrial application, because in those days there was a reason the world could develop this kind of technology greatly, because there was big the scientific technological battle between Soviet Union and the United States for spaceship. So at that time, to launch a very strong but very light the space structure, the composite material should be used. So that means the calculation for design is not possible by hand. So United States developed source code of calculation, so-called finite element method code, for free to the many organizations in the United States. That source code name is Nestran. So Nestran was a free code to the organization in the United States. These days, just some of companies, organizations, evolved that raw program for commercialization. So MSC is one of our company name, Sander Corporation, something like that. It is in Seattle, Washington State, near Boeing company. So it conducted many projects with Boeing, and that program was developed more advanced, based on the original the national. So we say it is MSC national. So we can see those kind of the excellent commercialized computational tool these days. So that's origin is start from the 1960s. Okay. So in 1960s, there was a significant advancement in the development of composite material. Okay. And the carbon fiber and the new manufacturing techniques developed. As a result, the composite material been, we can say it's started at those days. But historically, it's to 7,000 years ago. But the why intelligent and the advanced composite need to be developed, because conventionally here, this horizontal line is a specific strength. So, and this vertical is a specific modulus. That means a high Young's modulus line, this one, the high stiffness can be both. Right? So this metal group. So this is a weaker and light ones forms. But this lighter one, but higher strength can be found in this group. This group is beyond the metals. And this part is a CFRP, carbon fiber reinforced polymer, CFRP. This is one of the most prevailing and important composite these days. This is composite group we are using these days. We say this group as advanced composite, but just the composite material, as it can be found from natural ones to ancient ones, and even the traditional local houses made of composite, like the clay reinforced by some plants. Some plants can be used for reinforcement for building house in the traditional basis. And this polymer level. So this kind of build-up is very benefit to design composite materials. So this is very famous. This commercialized chart by HB is Oxford University. Cambridge is I'm not sure this name, but the one famous professor from UK, he developed this kind of chart. The research, and he commercialized these days this kind of the chart. This why this kind of chart is very important to design composite, because we can choose fibers and the matrix as we wish. And also this is just a constant temperature case, but if you pay for those information, in that case you can find many different level of temperature. The properties can be chosen, of course.
What is this technical and non-technical composites?
This one?
Here you have written non-technical ceramics and technical ceramics.
This one.
I'm not from ceramic background. I just want to know what is this ceramics, technical ceramics and non-technical.
This is fine ceramics.
Okay.
This is the conventional ceramics. So fine ceramics, that means it's more the fine particles before sintering.
And the composite part that we are referring to over here, this confers to FRPs, or this also includes CMCs and MMCs?
So MMC, I guess the MMC is maybe, I guess, this part MMC, I guess. And FRP may polymer based one around here, I guess. This is.
This composite picture is covering all the three.
Yeah. Just the conceptual.
I'm just comparing that strength part, the metals and FRPs and CMCs.
And so composite industry, its growth rate is enormous. So the all of the terminologies and technology sectors that I will introduce a series of lecturing, any one of those can be great business if you concentrate. Because there is no the saturated composite technology at all in composite materials, including manufacturing process, because still fully automation is not possible. So all of the points can be good start point for new business. So this 2018, 2019, 2020, up to here, because this is the documentation from 2023. So maybe up to here, that is the identified one, real one. That's the expected one, extended forecast one. So, but the overall, its growth rate is 12% per year. It's enormous because 7% growth means in 10 years its market doubled. This is 12%. That means 6 or 7 years the market size will be doubled. This is current the trend, but it will be accelerated. So any of technique needed in composite materials can be great business start point, even these days. Okay? So these blue ones is North American proportion, and orange block European proportion, and gray ones Asian Pacific, and yellow is South America, and Middle East and Africa is the blue ones, top ones. So that is current market. And composite is it have a particular strengths and weaknesses very less. I think weakness, or it has weakness, but its weakness is very narrow, I think, and which should be considered at the specifying stage. The composites are no means of the right material for abrasion. That is what we must keep in mind when we wanted to use composite material for any application. but major driving force behind it is a combination of reinforcement and the matrix. That combination is a pair of fiber or reinforcement type or matrix, those kind. It's a combination is enormously huge. So if you can choose the right pair, then it's, and of course it must be well manufactured. So in the laboratory it's very easy to make the specimen manufacturing, although it is expensive. But its volume is large, it's different story. It's very difficult. But if you can choose the right pair, in the case that performance is enormous. It cannot be compatible with existing materials. It's a very attractive point to be involved in composite material business sector. So if you want any required final property of material, this is composite material, including the monolithic materials. So composite material can be synthesized by yourself, if you can make, It's very attractive point. So it's very challenging, but very desirable to try, I guess. For example, if a final component needed to be fire resistant, so it's very difficult to find from natural material, but fire resistant and some level of stiffness and any kind of, but you can synthesize by yourself through composite materials. Okay? Fire resistant matrix. There are many fire resistant natural monolithic materials like ceramic. Okay? But the ceramic cannot be used as for that purpose, as it is, because it's brittle. But it can be toughened by using reinforcement. So you can create new ones. Okay. So in the 50 years ago, if we think of airplane, everybody think aluminum alloy or duralumin, something. That's all. But these days, everybody think, especially he is in the airplane manufacturer or the designer, then everybody think composite. So it changed from 10 years ago, due to Airbus. And this is a Boeing 787 body. Okay? Among whole materials, the half of it composite only. And still 10% aluminum, only 20%. It's a great change from many decades ago. So what is great contribution from Airbus 10 years ago? Because before that time, the airplane manufacturers never use composite as a primary structure material, because its manufacturing is so costly and its maintenance is very difficult. But because it is very lighter than aluminum and cheaper than aluminum, in some cases PMC. So those materials were used even before that time for secondary structure purposes, the interior of the airplane. But Airbus started to use very challenging of glare composites for its primary structure. So that made Airbus possible to make a huge aircraft is Airbus. So that was big change in airplane market. And composite is very important in airplane. Composite use the aerospace structure advantage, very light, and high fatigue resistance. So aluminum is very less durable. It is aluminum every time it is deteriorated due to fatigue. Aluminum cannot sustain at even at very low stress range, because aluminum it's the SA curve has no limit, as you see. So it's a slow, it's a decline. So after 2 million, 3 million, eventually 10 million, it will fracture finally. But still has its limit. Okay? If it is very low stress range, the steel never, still will not fracture at all if it is very low stress range. So differently from steel, aluminum has great the weakness in durability. But composite material is a high fatigue resistance is very possible. And the fire resistance high, and the corrosion is very important, right? Its corrosion resistance is very high. Aluminum is very weak to corrosion. Right? And composite can produce in complex shape because it is synthesized artificially. And most ironically is mostly the man-made work is needed. That means it's expensive. So fully automatic is not made yet. So, but due to that kind of process characteristic, complex shape is possible. And a large piece also possible because it is man-made. Process is included. Okay? Disadvantage is very expensive, and the strength property is not equal in all directions. And so it's a reinforcement material direction is affect the performance, and the maintenance is very difficult, and material quality depending on production, and no standard quality. So it must be overcome. And the materials constituent materials along with a process by which they are combined determine properties of finished accomplished part. So that means there are many choices among fibers. So here is we are talking about just advanced fiber only, not conventional fiber. So advanced fiber is E-glass is most the common ones, the cheap one, common ones, and the carbon fiber and the aramid fiber, natural fibers is increasing to be used these days. Anyway, because recycle issue. So these fibers, advanced fiber means it's the dimension issue. The diameter of any material, if the diameter, it's a fiber type, if you think the kind of cylindrical shape, if you can make as thin as you can, that means the smaller diameter, the higher stiffness. For example, this glass is the same as conventional glass, but conventional glass, it cannot resist up to 20 megapascal, it breaks away. But if you make it very thin, very small dimension, so conventional e-glass is 100 micrometer, but these days e-glass is about 30 to 50 micrometer. So 30 to 50 micrometer means your hair, its diameter about 50 micrometer. So that amount of e-glass, its strength is more than 1 gigapascal. That means it's greatly increased if you can make in a small dimension, because that means it is because if you make a very small dimension, that means in small dimension, large defect cannot be included. That's why it is highly stressed. Okay. The very bulk glass, there can be huge, the big, the air pocket can be included, for example. It is kind of crack. But if you can make smaller and smaller, then the big porosity cannot be included, because in the processing, it is just failed. So you cannot produce. So that's why fibers, advanced fibers are very, so, what? Can you hear? Okay. Pore size. So I have to go faster. The carbon fiber is less than 10 micron. It's 5 microns in diameter. And if it is viscose type, very very short fiber, we say it is viscose. Viscose is just 2 micron or 1 micron in diameter. So that's why it is very strong, very strong. So, so there are so many different type of advanced fibers these days. That means you can have freedom to choose one of those for your design purpose. And the resin is the one of polymers, long chain like molecules. There are some of plastic, some of set. Those kind of resins are existing. And if the glass fiber is reinforced, then we say it's a glass fiber reinforced polymer, GFRP. If carbon is reinforced, then carbon fiber reinforced polymer, CFRP. And etc. We need to use a filler or additives, okay? Not just a matrix and a fiber. For processing purpose or some kind of stability of performance, we need to add filler or additives in addition. And there is intermediate materials. So this is a little bit a detailed part of manufacturing included, not just big aspect of reinforcement matrix only. There are more materials needed at a time, and some technique is needed. Then the reinforcement. So not just one directional or long fiber or discontinuous fiber. If it wanted to be shaped in 3-dimensional or something like that, in that case, you can make a 3D preform, like making your sweater. So you can make it's the same technique is used for making sweater, the cloth. Okay? So by using advanced fibers, so you can make 3-dimensional the structures, and in the process, that the free form will be the wetted in the resin, something. It's a kind of process. Anyway, the 3D free form can be used, and this one is a carbon fiber pre-impregnated with the resin. That kind of form is, we say, is a pre-prego. Pre-prego looks like a tape, just the 3M tape. It is the pre-prego. It can be used as a raw or material form to make special shaped compressed material. And the BMC terminology. BMC is a bulk moduling compound. So this is a mixture of short chopped fiber, resin and filler used in injection. So that is BMC, and also SMC. SMC is a sheet molding compound. Okay. This is intermediate material. That means it is not very basic material, not a final composite material. It's between intermediate level materials. Okay. And also there is a thermoplastic preparator can be purchased on the market to make your own composite materials. And the benefits to use those kind of material, intermediate or so original fiber matrix, various kinds of material shape can be used for composite material processing. The benefit, durability maintenance, and added functionality can be adopted as you wish. Okay? And the design freedom is guaranteed. Okay? Using composite material, there are some challenges, because the one most worrisome is cost. It's expensive. Okay? Composite material can be more expensive than traditional material. It's much more expensive than traditional material. This is because reinforcement in composite material is often made of high-cost material. Not just that. The cost is okay. That can be covered. But the problem is manufacturing cost is so high. So that means if you can invent good manufacturing method, then it is enormous business. Still, it is being tried. So RTM, so there are also ITM processor. Because every kind of modification manufacturing method is patented. So if your developed method can be adopted by big manufacturing company, then every daily they will pay you for your idea. Okay? So it is impossible at the desk. You must and the testing as result. It is needed to develop new manufacturing cost. Anyway, cost is manufacturing is the main contributor, and the sensitivity to moisture. That means corrosion is no problem, but the sensitivity to moisture. This is the case of polymer materials. Polymer is very weak to moisture, and barrier is limited to PMC, and so this is brittle. Brittleness. B is missing. Brittleness, and the manufacturing complexity. So manufacturing is difficult. That means, and the advantage lightweight, corrosion resistance, high impact resistance, thermal. That we need material like the good thermal conductivity, but poor electrical conductivity is needed. Sometimes we need low thermal conductivity but high electrical conductivity. For example, if you think LED light sink, the heat sink, in the case mostly we use aluminum alloy. Because it is lighter and as a heat sink, it has very high thermal conductivity. Right? But the problem is it is very good very good electrical conductivity. Very good electric conductor. That means so aluminum can so you can get some kind of electric shock when you touch it. So if that heat sink is good, very excellent thermal conductivity, thermal conductor, but very poor electrical conductor, that means it will be very good heat sink. It's very important even for micro scale, the chip industry. Okay, so that is those kind of material inventor and patented materials. Very, very expensive. But if you can make it based on nanoparticle based composite material, you can do. Then in the case it will be very nice. For example, if it's a very poor thermal conductivity but a very good temperature, very good electrical conductor, in the case very few, 4% of carbon nanotube can be used together with the resin. In the case, it will be very good electric conductor, but very poor thermal conductor, something like that. Anyway, some kind of combination very important for material design and applications. So application can be found everywhere. Especially aerospace, automotive, construction. So there's massively the consumer of composite materials. So as said before, the aerospace is one of main material already. So lightweight, durable, for fuel efficient, something like that. And the automotive case also, because it can improve fuel efficiency. So it is becoming one of the main properties, the main materials becoming, not the completed one. Because so far you can find just a small number of parts made of composite materials for automotives, except very expensive parts. But still aluminum, now it is converting to the composite materials for automotive parts. So BMW i3 electric vehicle with carbon fiber reinforced plastic. Also it is expensive, but BMW car is it can cover the cost of carbon fiber reinforced plastic. If it is cheap car, it cannot use CFRP, but if it can sell at just a few slides. And the construction is that the lightweight is not important, but durable and corrosion resistant is very important for construction. And renewable energy part, wind turbine blade, electronic, sports foot, and space So it's very widely adopting composite materials as the main materials. In the aerospace case, it can be break down into many parts. Each of the detailed sector use different composite materials. It's not one type of composite material. So aircraft structure and the fuselage and the wings and the tail fin and the door bearing, rotor blade, jet engine components, all of parts use different type of composite materials. But mainly they are adopting composite materials for their materials. The automotive parts is the interior application, dashboard, console, seat and trim already, and exterior parts, body panel, bumper, aerodynamics purpose. And the structural components, chassis frame, crash worthiness purpose. And the thermal acoustic insulation, powertrain components, EV battery includes so far, so on. And the construction parts, cladding, facades, roofing, insulation, corrosion resistant structure, prefabricated composite panel, utility pole and structural support bridge deck. The renewable energy, wind energy, turbine blade, solar energy, hydropower, wave and tidal energy, geothermal energy, piping, KAIST. So there are so many different kinds of, but for example, turbine blade, I involved in the turbine blade development for aircraft for 3 years. For serious, based on ceramic matrix composite. So that means I just engaged the recent years, 3 years to develop a turbine blade, but there is companies to develop turbine blades for their business for 20 years, 30 years. That means what I mean is even one of part can be your lifetime business issue. So design method, manufacturing method, and the final dimensioning finish, is everything is very important for each industry. The electronics is a PCB and heat sink and the thermal management problem issue, and the enclosure and casing, and the battery housing, energy storage, and the antenna signal transmission components, display wearable technology. For example, antenna itself, so one company near Inha University in South Korea, so they are making a revenue $0.5 billion a year, just the antenna. As composite materials. So you can study all of those at a time. You don't need to do that. You can focus just one of those if you have great interest. Then you can focus one of those. If you can contribute, then you can make great money. So this is our last slide of the lecture one. So the future trend and innovation in composites is differently from today. The recyclability is very important issue these days. So if you develop a new composite system, in the case, many times you will be asked how about to recycle that material. So that recyclability is one of the future issue. And another one is smart composite. So that means that composite, that material is a live one. So that means like a skin. It can sense it can actuate, the sensor and the actuator can be embedded into the the materials. So smart composite is another issue. And the self-healing composite, that means if there is a micro-scale damage occurred, then self-cure. It's especially for bridge construction in civil engineering. They are finding those kind of things, or building materials. And the sustainable materials, so biocomposite like plant fiber reinforced material for eco-friendly solution, those kind of things are these days and the future issue for new composite materials. So this is about the introduction to composite materials. So after this lecture, we will try to see the one by one, although those are another large scope, but I wanted to introduce you how composite material is important in these days industries, and so why you are studying it in the university, because you wanted to make the good money and have good technology. That technology can support your lifetime. Yes. So you must have some direction. What should I spend my time, my valuable time? In that case, I strongly recommend you to choose one of those terminologies. Then you can find your way, because it is just a starting point, not a saturated point at all. So let's go together with me through the 10 more lectures to see what kind of issues existing in composite materials. Right? Okay, this is the end of next one. Do you have any question or suggestion? Sorry about the poor microphone. Usually I don't use a microphone when I give lectures. It's not familiar with me. If you don't have any, you have? Yeah.
On what basis we are classifying the short fiber composite and long fiber composite and continuous composite? Means like if we have a 2 meter big structure and we are putting half meter of fiber, half meter length of fiber in that part, so we will call it as a continuous composite, or we will call it a
I did not see that kind of case because the long continuous fiber is used to, or chopped fiber used to, is just decided, because depending on its the part size already. So it looks like a fault point, not intentional point. So I mean, if you want to make a 2 meter structure, then you never use the half length of fiber into one component.
there is any ratio on what on that basis we can define that, okay, we will call it as a continuous composite or we will call it as a short fiber composite?
Must say with raw materials. If you use as an ingredient chopped fiber, in the case it is chopped fiber reinforced composite material. Yeah. If you are very long fiber, it has kind of a winding already. So in the process, you pull that long fiber all the time. Then it's a long fiber reinforced composite. It's something like that. So this continuous one is different from chopped fiber. This continuous one is must be aligned differently from chopped fiber ones. In the case of well aligned, but its original raw material is already chopped. So because it's a long fiber is prepared, but during manufacture it's chopped. It's chopped. It's continuously. Although its alignment is very
Also depends on the component part that we are manufacturing. Like if we manufacture a part that is
correct.
like the size of the screw,
Yeah.
then the length of the fiber is very much short and we can define it as a chop. But if the fibers are made according to the whole length of the complete pattern, we say it as a long process. Another question is that you said that complex pieces can be made through the composite manufacturing. But if you see the traditional composite manufacturing process, then it is very difficult for us to get the composite part. Either if we will get the complex composite, if we want to manufacture complex composite, then we will have to do the post processing. After the manufacturing of composite panel, we will have to do the post processing, and that is very difficult to do in the composite. So how we can
The reason is complex shape can be made of the composite material. Yes. So I said it's kind of man-made, manual work is needed, right, for processing the composite. So the mold is prepared. So any kind of shape we wanted to have. And then, so very complex shape can be prepared, right, as a mold. Then manual work will be done on it, okay, not by the fully automated machine. Okay. By semi-automatic machine is needed to do some work on it. So any kind of shape can be accomplished. Okay. So that means, yeah, so that's why it's expensive. So that's why I said it's ironically. Ironically.
the properties are different in different directions for composite material. It's anisotropic. So it was known from 1930 onwards composite materials are there, but still the researchers are solving how can we improve this anisotropic or composite materials?
Isotropic composite materials?
Yeah, these different properties in different directions now. There's a major disadvantage for composite materials.
So the randomly oriented one, it's isotropic property after all. Right? So the purpose of that kind of composite material is the target is different. Not specific directional. The high stiffness is not target. It is overall property. It's corrosion resistant to the weight, lightweight, but the reasonable stiffness in the case. So if you cannot find appropriate monolithic material for your purpose, in that case you can mix it, not for the specific directional stiffness. In the case, randomly oriented one is needed, and its effective isotropic property can be easily calculated from mechanical engineering. Okay. Even the computation program support you is very easy. So, okay, so let's see the next lecture. Okay. So, all right, thank you so much. I'll go quickly for the second lecture because actually I prepared this for 1 hour, but I'll go through 20 minutes, okay, from now on. Because there is no equation at all, because I have not included any kinds of computational aspect. So it's very easy to follow. And if you have any the question behind it for development or calculation, any kind of things, so you can send the email to me. Okay, then I'll respond. Actually, the type of composite material is our second topic. Here you can say the PMC, CMC, MMC is the most typical classification. So actually, if we can say it's a intermetallic matrix composite, there's one more thing. But it's very rare case to be adopted, so it's deleted here. So PMC is a polymer matrix composite, CMC is composite matrix composite, MMC is metal matrix composite, and the hybrid composite is mixed as it is, as it means. So type of composite materials is a PMC case is bestly used in aerospace and automotive industries because this PMC-based one is a very excellent properties can be expected, but its manufacturing technique relatively well established. So as an example, the mobility use the carbon fiber based matrix is very popular, but construction case glass fiber based polymer is most commonly used. And the metal matrix composite case, as a base material, the matrix material, aluminum is mostly used one. So aluminum reinforced with the silicon carbide, kind of this can be improved its stiffness and the weight can be reduced, and so the durability can be extended. And the ceramic matrix composite case, so silicon carbide reinforced with the silicon carbide. Usually silicon carbide reinforced. Silicon carbide is as a fiber form. It's most the famous the silicon carbide fiber manufacturer is in company in Japan. So it's Nickelon. Nickelon is most famous one. So usually Nickelon fiber reinforced silicon carbide, those kind of things. So actually, that is one of my main material or system studied in PhD thesis. So if you have education about that, just email me. Then I provide some documentation on it. And as a base material of polymer, there's two classifications. One is thermoplastic, another one is thermosetting. Right? Thermoplastic is good for recycling. Thermosetting is not. So it's just volatile. Right? So thermoplastic one, as a thermoplastic can be heated and softened, then molded and shaped, so it can be recycled. So thermosetting is irresistible chemical bond reaction bond. So cross-linked and curing dual process to change phase from liquid to solid state. The cross-linking enables to eradicate component remelting with the application of heat. And the benefit is the recycled. So this is not recycled. So Uh, I think thermosetting based composite is more better performance, I think, but due to its weakness in this recycling is a little bit difficult to be adopted these days. And the classification based on reinforcement structure is a particle reinforced, okay? And this is short fiber reinforced. And this is unidirectional long fiber reinforced. This is bidirectional reinforced and the laminate composite and the open composite. This is a modernized one, okay, compared to the unidirectional laminate. And braided. So braided composite also this is these two ones, woven and braided one is most advanced ones among them. And the fiber reinforced composite materials. So glass fiber, carbon fiber is glass fiber. It's and the aramid fiber is just used for very special textiles. So Kevlar is one of the aramid the fibers. So DuPont made available in early 1970s. And it's very good for high strength, good resistance, or something like that. So aramid fiber is very well used for fishing rod or golf club. And the natural fiber reinforced composite extremely popular for many uses in recent years because it's eco-friendly. Due to government policy and environmental consciousness, the use of natural fiber in polymer composite increased, especially in France. So polymer matrix composites are material made by embedding strong staple fiber or particle within polymer. So this PMC group, its mechanical property strongly depend on the fiber performance. So polymer, as a polymer matrix, the PMC backbone is just binder. It's kind of sticking together of fibers. And thermoset, as you can see, the epoxy. Epoxy is the most widely used one. Epoxy, polyester, vinyl, ester resin, or thermosetting polymer are solidified irreversibly when cured. And the thermoplastics polymer is polypropylene, ketone. So very difficult to read. And the hybrid matrices. And so glass fiber. The glass fiber is mostly the bestly used one these days. So if we say FRP, in the case in the commercial market, everybody thinks reinforcement is glass fiber. There's carbon fiber ones, aramid fiber ones. Is well being used these days. And the advantage application PMC. Lightweight, high strength, design flexibility, corrosion resistance. So the overall the comment can be found on slide, so you can ask to download this slide from the NIT Jalandhar professor. And conclusion, as a middle conclusion, the possibility of a polymer PMC, as a PMC has revolutionized the industry by providing exceptional strength, lightweight, design flexibility. And the PMC, the vital role in shaping the future advanced material sustainable engineering solution, especially for the future of the personal mobilities, is trying to use bestly this kind of material. So property and application sectors, strength and stiffness, corrosion resistance, design flexibility can be classified issues. The strength and the stiffness of polymer composite can be engineered to have exceptionally high strength to weight and the stiffness to weight ratio. And the corrosion resistance is very important to the application. So these days, because strength or other flexibility can be matched from any kind of advanced materials these days. So corrosion issue or especially electrical or thermal properties more concerned to the manufacturers these days. The CMC case, CMC is exceptionally high temperature stability is preferred, right? And the thermal shock resistance, thermal barrier, those kind of things, the CMC should be considered. And where corrosion resistance and the application. So, CMC is because as I said in the lecture one, as my academic background, this is the main topic of my PhD dissertation from Corning and DuPont. And at that time, I was involved in Oriental Express project. In the case, so there's no lubricant for ceramic engines or something like this. So, so unique strength is it can be used to extremely high temperature environment. Okay, so over 1500 Celsius also possible, 1500. Okay. So thermal shock resistance is very important issue. And the reinforcement and processing so for CMC. It's continuous fiber particulate reinforcement processing method, that kind of issue be examined. And high temperature capability, thermal stability, thermal shock resistance, and mechanical integrity. So this kind of CMC materials, manufacturing technique is most sintering is included, and traditional pot maker is the one of major manufacturers these days. So ceramic pot manufacturers, they are going two different ways. One is for fine ceramics to semi the electronic ceramic materials, or the high temperature structural materials. Okay, they are finding either one. But I think the ceramics for electronics industry is almost is technology saturated. So if you are thinking about the ceramic industry for future use, I strongly recommend the CMC level, or especially nano particle reinforced ceramic is very important for the bio compatible or artificial bone industry, or so even any kinds of mechanical component industry is need those kind of goods. So, so strength and stiffness. This is metal, and this is MMC case. As you see, the so although the metal matrix composite has as a major material of composite metal, that means its property in volume ratio is about up to 80%, 7 to 80% is metal. Only less than 10% or 15%, those will be reinforcement. In the case, its tensile strength can be almost doubled, and the elastic modulus can be doubled. So the cost a little bit increased, but its advantage can be found easily here, right? And hybrid composite is combining strengths tailored performance application as needed. So the mixing of the more constituents can be combined together, not just the two materials or three materials. So multiple ones can be combined too, like Korean bibimbap. It's so everything you want to see the special property, then you can add and the sintered or the manufactured, then check the property. And in the case you need to design your test setup, and you need to understand the measurement scales, and you need to understand how to calculate overall effective properties needed for you. So that means you need to develop mechanical model to evaluate your newly sintered ones. So that means so a single research is single department research is not integral, I think. So interdisciplinary team is needed. So mechanical engineering and the material science engineering and sometimes physics, because of very nanoscale research also needed. So in that case, you can make a very the strong team to develop some kind of composite system. Okay. So combined material advantages, you can find recoverability. Also, I have to finish it. Okay. So challenge. So that is about the PMC, CMC, MMC, something like that. But very interesting things, these kind of things. So to make the theoretical model to evaluate effective modulus or expectation of ultimate strength or the toughness of that material, you must develop your theoretical model. And you can design the composite, because just to use that theoretical model before fabrication, before choosing your constituent or volume percent, you can check which one will be best. Of course, it is different from your final choice, but you can reduce your number of tests. Okay. But if you just think, okay, I can use a computational program to evaluate in case it is that is kind of a computational model, means just one model gives you just one result, like a test. Okay. So it is not appropriate to check the influence of any special parameter, okay? Because just one point give you as a result from computation. So that's why you need to collaborate with the mechanical engineering model, a theoretical model developer, or the professor in physics to make the theoretical model. Then you can save great time to develop optimal composite materials. Because if you don't imagine, but in my experience, I say the most important thing, the delicate one, is coating export. That means the fiber or reinforcement, it cannot be embedded as it is. It must be coated to resist something. So that means it is a very special part of chemical engineering or very special part of the material science. So it's very difficult to find a good specialist in coating materials. But I can say to make very favorable interface or interface property from your composite material system, you must find a good coating specialist. Then you can, because the ceramic metal composite case in my days, so one nickelon, it is 3 times coated. So with different the material system, so that it can in the very toxic chemical environment, something like that, or it can improve the toughening characteristic afterwards. So I should emphasize PMC, MMC, CMC. The exact PMC. PMC is listed in the sense, but MMC or CMC, the fiber coating is very important to make the final property. Okay. This is about my very short second lecture. So if you have any question, then yeah.
Sir, what kind of reinforcements can we add to the metal matrix component?
So in my case of silicon carbide fiber.
So in fiber form we can add?
Both of those. One is fiber form and the particle form. Yeah, I tried to with the Hyundai Motor Company to make aluminum matrix based the rotor, brake rotor. But aluminum itself, it cannot be used. It is the wearing too fastly, right? And its melting temperature too low. So we added the silicon carbide for particle inside. So it can be increased, but the final performance is not so great. So it is not used. But except I have experience to work with the Hyundai Motor Company ceramic matrix composite rotor. So it's so I gave them the three patents for CMC rotor. But so far I have not seen the Hyundai ceramic rotor yet. But at the time, the Porsche or those other companies already they use ceramic rotor. It's very expensive. The one set of rotor is about $5,000. So it's very expensive. At the time, Hyundai Motor Company asked me they wanted to make just $1,000 rotor. But it's very difficult to make. Anyway, usually there are many the material change potential requested by industry. So you can find if you have any special the interest in any part, then just think, okay, this is best material, or it can be replaced by new one. But the new one, if that property is like this, then it will be much better. Then how I can make it? Just composite is the solution. You can make it. So I'll meet you at the lecture tomorrow. Right? Thank you so much. today my responsibility is to give lecture 1 and lecture 2. But after finishing my talk, I have a third one. You need to lecture 3 too today. So differently from my talking previous, I will give you the lecture 3 today. Lecture 3 is actually this is more familiar to me in my ordinary the work on the composite material mechanics. So this is the basic ones toward those kind of computation. And the title is Key Terminology and Concept in Composite Material Mechanics, I guess. So lamina and its characteristic, we are using single layer or fiber orientation or material properties. The single layer means just a single plate, Of course, that single layer is a lamina. Lamina is a single thin layer of composite material. So typically consisting of fiber and embedded inner matrix. So its thickness is very thin. As you see, the fiber diameter is just at most 100 micrometers, something like that. So after the infiltrating with a resin over it, its overall plate or ply thickness would be 100 at most 300 micrometer, so 0.3 mm, or if we use the thin one like 10 micron carbon fiber, something like that, in the case its practically will be thinner, so in the case 100 micron, something like that. So a single layer cannot be used for mechanical structure. It must be stacking together. And the fiber orientation means each layer may have different fiber orientation, but single layer has unidirectional, unidirectionally aligned the orientation is common one. And the material properties means each lamina has its own material property. That means it's elastic modulus, shear modulus, Poisson ratio, like the monolithic material. That means inside there's two ingredients for matrix or fiber. For example, in the case of fiber has its own material property, and the matrix has its own property. So that means we should have some way to estimate overall, I mean the effective material property for ply. So that is very, the most simplest form is we say rule of mixture. So fiber orientation and angle. Zero orientation is a fiber aligned with the load direction. So load direction, usually we say is x direction. It's a load direction. If x direction, the load direction is aligned with the fiber orientation, that means we say that ply is 0 degree orientation. And that fiber oriented direction, of course, it can provide the maximum longitudinal strength and stiffness. And the 90 degree deviation, so the transverse direction of 0 degree orientation is 90 degree orientation. That's fiber perpendicular to the road. Yes, and enhance transverse properties of composites. And otherwise, we may have 45 deviated orientation away from the road direction. The case of fibers at angles improve shear strength, and the torsional rigidity of composite can be strengthened. So laminate theory and the laminate stacking sequence terminology is a stacking sequence means the order of ply orientations. Usually the ply orientation is recorded as an angle. It counted from the bottom. From the bottom. If it is unsymmetric, it's an unsymmetric one. That means the ply usually we make it's a middle plane. In the thickness, there's a middle plane. The middle plane it would be the interface most of the time. That interface, if it is a symmetric plane, in that case, the stacking sequence above that plane and below that plane, the sequence will be the symmetric, right? The 0, 45, 90, then 0, 45, 90, something like that. In that case, we count that from the middle, not from the bottom. So from the middle, 0, 45, 90, and we make the S subscript. So those kind of stacking sequence, the record can be symbolized. And the symmetric means that it has a symmetric plane so along the thickness, and the quasi-isotropic means a special layer is so equal stiffness in all directions. That means that a ply will be in the different various directions will be symmetrically stacking. Okay? And ply and lamina. Ply is a single layer of composite material. It's a building block of laminate. Lamina means a thin layer with a distinct fiber orientation. So multiple laminae from laminate. And the thickness is total. As I said, typical range is 0.1 to 0.3. That means usually 16 applies one of most the common cases as a complete plate, composite plate. That means the 0.1 times 16 means 1.6 mm. It's a very thin composite plate. You can imagine. At the 0.3 case, that means it's a 0.3 times 16. That means it is about 5 mm thickness. It is the moderate thick laminate, say. So, constitutive equation. The constitutive equation is simply for undergraduate level material, the material mechanics. In the case we say it's Hooke's law. Hooke's law is a relation described between load and deformation. So for one-dimensional stress equals Young's modulus times strain. It is simply is the form of Hooke's law. So it's a general terminology. It's a constitutive equation. This constitutive equation of a lamina can be calculated systematically by using the rule of mixture. Here is the 1, 2 means 1, 2 is a principal direction. The principal direction. The 1 is usually is a loading direction. Many times we say. So elastic modulus E1, E2 is a stress corresponding to sigma xx, strain epsilon xx, something like that. So this kind of the stress, strain, and the modulus, and the elastic shear, and the Poisson ratio can be calculated by using the force balance equation by using assumption of iso or force condition or iso strain condition. From those you can calculate many of simple or basic equations for lamina. So if you have this kind of laminate properties, that means after that you can neglect the oriented direction of fibers. That means E1, E2, G1 to G21, something like that. That is your effective modulus of that composite plate. That means after that, it is you can see no more any fiber or matrix separately. You can just treat it as a continuous medium with anisotropic property. So that means you are ready to make a computational model based on that continuous medium assumption. That continuum has E1, E2, G1, Nu1, something like that. Okay? Overall, you can make this kind of model for FEM. So maybe the ex-student Dr. Vivek Dimoli will give you about computational method.
So actually next tutorial is based on this.
Yeah. She is well trained, many years. So she will give you about computational technique. And so if you in your model, if you don't model any kinds of fiber or matrix separately, then we say that is a macromechanical analysis in the case. But if you should identify this is fiber, this is matrix, in the case of we say it's a micro scale, micromechanical analysis, something like that, right? And the macromechanical analysis is just anisotropic plate theory. Okay? The classical lamination theory is used to make equivalent laminate properties. Assumption is classical lamination theory makes assumption, mechanical material behavior and the geometry of lamination. That means there is no distinction between fiber and matrix, something like that. And the application, CLT is applicable to wide range of lamination. So through this kind of calculation, you can estimate the overall behavior of composite material structure. And classical laminate theory like this, assumption is a lamina and the scene and perfectly bonded together. That means this is very, very ideal because as I said in the previous lectures, the most weakness of composite material plate include defects. It cannot be avoided. And that defect cannot be neglected because of vastly many defects can be found and the shape of that characteristic of those are very different. So you must know those kind of distinct weakness or caused by different damages. Not damage, it's originally manufacturing the fault. It is not fault, but because it cannot be avoided. Anyway, there are many incomplete bonding existing, but there's a perfectly bonding together. So this is a very huge assumption. And so accordingly, there is no slip between different plies. Okay? It's also very difficult. So it is, without this kind of assumption, simple calculation cannot be impossible. So that means with that kind of very ideal assumption, your calculation means a very ideal behavior. So you cannot expect the final structure will behave like this in precisely, just the overall behavior like this. If you worry about some premature failure of data structure on the working, in the case you must conduct micro-mechanical analysis again in addition to macro scale analysis. That's why to develop and to build composite material structure require tremendously computational works. So that means although you can make its behavior cannot be predicted before the advent of computer development, advancement. Right? So that means I believe in 1983, that year was the first time I could see personal computer. 1983. But as I said in the previous lecture, so 1960s is first decade to develop advanced composite materials. That means almost 20 years distance between first the drastic application of composite material and the real advent of modern personal computer. For example, I completed my master degree in 1985. But at that time in my laboratory, there was at KAIST at that time. So one of my senior colleague, he studied some computational mechanics, and she calculated just a spherical void on the ground. And if on that above that surface, if there is some pressure distribution, like a huge truck or a vehicle, something like that, in that case, she wanted to know the stress distribution on the ground. To calculate that problem based on finite element method, he used the Korean government-based supercomputer at those days. And of course, because KAIST is supported by Korean government, so the computation fee is waived, but the bill is given. So when I saw how much he used that computer for 1 year, that time it was about 100,000 US dollars at those days. That means in Seoul, Gangnam areas, one unit of apartment was 50,000 US dollars. That means 2 apartments he used for calculation. But that kind of calculation you can conduct on your cell phone these days, very easily, very easily. So that means how fast development of computation tool can be expected. Right? So if you want to do better composite material engineer, you must seriously think you gotta know how to use computational mechanics. You don't need to program by yourself, but at least you need to know how to run that program, how to constitute your model based on that. So it is very needed. And the micromechanics of composite means, as I said, constitutive model include the fiber scale and the matrix scale should be considered, because only in this case you can consider interface between them. So that means in micro mechanics model, you can think the interface between fiber and the matrix. That means if that interface have some kind of defect or some kind of different coating over fiber, in the case it can be evaluated from the computation, so that the more exact detailed behavior of composite material can be evaluated. Your test result after lap scale specimen fabrication, it can be compared with your computation results. The overall rule of mixed model is not sufficient to compare your specimen test results. So it's very much careful. And analysis part, micromechanical analysis help optimize the design of composite itself. So to develop composite, you need a micro scale computation mandatorily. But if you want to just build your structure based on existing composite material, then macro scale analysis can give you amount of knowledge. Okay? You don't need to micro scale case, okay? Except to special. This is a stress strain behavior of a lamina. Okay, lamina. So it's behave like the ordinary monolithic material. Okay? But if your specimen make from the different style of manufacturing process, then based on the same constituent composite system, you get to know how different of their test result. It's very different, very different. Because the composite material case, if you simply you think the brittle fiber and brittle matrix case, even in the case it looks like this kind of very the conventional behavior can be obtained. In the case, the toughness must come from, in the case, toughness must come from defect. It's very ironically true. So that means the fiber itself has no ductility. Matrix has no ductility. But brittle fiber reinforced brittle matrix composite has ductility. Where does it come from? Ductility means energy dissipation. That energy dissipation must be from the very micro scale mechanical friction. That means that the friction comes from matrix crack or interface crack between fiber and the matrix, or fiber break inside. So those kind of defects or damage can give you energy dissipation in that system. So that means all of ductility from composite material comes from damage, mechanical behavior, not the material itself. So it's a mechanical problem. Okay? So it is very interesting, but it's a more difficult case is obtained because if you are using the steel reinforced concrete case. In the case of steel has ductility itself. And concrete is brittle, but concrete can be cracked. And the fiber and matrix between them, the interface can be cracked. That interface crack. But it's difficult to get a break of steel fiber in the case. But that steel can be plastically elongated. So that means plasticity can give you energy dissipation. So it's a very complicated case. But if you get a more delicate model of composite material system, so even resin or polymer, it has also its energy dissipation state, like a crazy, right? So crazy is different from yielding. crazy can be included in the model. So even PMC, if you want to get the most accurate mechanical model, then you must think of various interdisciplinary concepts and knowledge. So, that in the case you can get writing SCI paper level. That is research level. And stress strain behavior. So elastic region must be found. But yield point means internal damage occurred. It's the first point of yielding in the sense of composite material. And the ultimate strength is over final failure. Means it can be calculated and tested from the specimen. And the classical lamination theory is you can calculate A matrix, B matrix, D matrix. Okay? So here is a D matrix means the relation between curvature and moment. That is D matrix as a coefficient. And the B matrix is in plane and bending behavior couple. And the A matrix is conventional, the constitutive equation matrix. So those can be calculated from computational model. And laminated stiffness and strength. Stiffness, strength, stacking sequence is the terminology of study. Stiffness is laminated stiffness, determine the stiffness of each individual laminate and the orientation relative applied load. Strength, laminated strength is determined by that. This kind of description means to predict stiffness, to predict strength, to use stacking sequence, what kind of parameters should be considered, those kind of described here. And the laminate stiffness and strength calculation. Calculation is involves CLT, classical lamination theory, equation, and material property to predict stiffness and strength. And the factors means stiffness and strength are influenced by fiber orientation, layer thickness, and the material property. So those kind of things are inherent material properties oriented, right? So those kind of things can be used for composite material plate calculation, but more important one is this one, laminate failure criteria. Because 2 years ago, I gave the one project for Samsung Electronics. That time they had the problem in their research center because previously the polymer was not used for oval casing. So they are large scale LED television, something like that. But these days, as you see, all of that kind of frame is made of polymer or engineered plastic, and on it the aluminum like plating, the metal plating on it. So it is not metal; it is polymer. So their development station, they calculate the large scale frame of TV. So it can bear the weight and the summer loading. They can calculate, but they got to know something strange, because after 14 days container storing from Korea to Middle East, then that polymer got degraded by summer loading. So it doesn't look like a new one. So so in the case they lost their the product quality. So they asked to improve the design to the research station. but they have no idea about the failure criteria. So when they came to me, so I asked, so far, what kind of criteria have you applied to calculate? Then they said, von Mises criterion. They said, von Mises? Von Mises criterion is for metal. It's a metal yielding criterion. So it cannot be used for polymer like or composite materials. It cannot be used for. But in calculation steps, in any kinds of companies, they are confusing about criteria. You must know the failure criteria to calculate it's a lifetime of structure. Okay? So inside the fiber fracture should be calculated, and the matrix cracking level should be known. And the delamination, this is a very serious one, because delamination means it is a multiply stacked one. So between ply and ply, there's an interface. Interface is a bonding line. Bonding line always is the most weakest plane. So during using, there is a it is a delamination between adjacent lamina. So that criterion must gotta know. Otherwise, if it's that plate, composite plate got compression, then that delamination area will be. It's very difficult. So then, what will be very different issue about that? The constraint is very important for composite material plate. Then you cannot make a final shape of a plate all the time because it has a different edge. If some cases you need to machine, you make a hole on your composite plate, hole. So I mean the machining of a composite material I'm talking about. So the interface is very important, but it's a perfectly, you try to make a perfect bonding between them, but even in the same temperature, it is different from manufacturing temperature. That means temperature gap existing already, but it is well equilibrated inside, internally. But if you make the free surface by machining, that means there will be step between different plies. So after you gotta know if you make a hole, then that hole will not be the circle. It's a retracted shape. But you cannot polishing by sandpaper around it. If you try to that, you will make a final failure of that plate. It cannot be used. That plate is very expensive, but you permanently damaged that. How you can make a final machining of it? How you can make the less internal stress distributed the plate? So there are many issues in the end. So just imagining calculation, manufacturing, even after good manufacturing, you have another story. So composite material case, you must study that system together with testing all the time. Testing. Okay? So micromechanics of composite, Rule of mixture, Halpin-Chai equation is one of most frequently used failure criteria, and the stress transfer. That means a fiber break somewhere, then that fiber cannot transfer the force through the fiber, then that force should be bypassed through the matrix, then matrix will get stress concentration, that concentration can make a matrix crack. In the case of that, overall failure will be started. So you must think those kind of things. And a few important failures here is composite motor. So maximum stress, maximum strain, GIO criterion, Hessian criterion, or many other things. This is a second order tensor equations. So you must know about that. That is a generalized form of the von Mises criterion for metal. There's a few important experimental characterization, tensile testing, flexural testing, shear testing. So even though you wanted to test based on the composite material specimen, there's another problem. Is for metal, steel, aluminum, those kind of conventional materials, there is a well-established test method found from documents, STP or ASTM, those kind you can tell. But for material of composite, it is very less. Many times it is not well established. That means you need in-house equation by yourself, in-house test method by yourself. In the case, that test method must be justified by yourself to persuade others. Right? That means tremendous of knowledge is needed to develop composite material, manufacturing, structural analysis, many of those. That means I can say it is beginning stage of material development. So any terminology introduced in these lectures can be good point of huge business in case. So it's very good chance, good, I think it's a good, very nice opportunities as an engineer. But this must be known. Practical testing, practical build-up by yourself, and practical calculation and theoretical calculation or mixed calculation, semi-empirical calculation should be discussed with your colleagues. Then you can make a great composite material product. Then it can contribute to your life successfully, and country can be contributed by yourself. So this is about lecture 3. Have any questions? It's no. Although there is no equations, but this is one of my major expertise. So calculation is very interesting and very nice to know and needed to know, but you don't need to understand fully all of this, but you need your colleague who is familiar with this kind of modeling and analysis. Okay? Thank you so much.
and metal additive manufacturing, welding, and he do lot of things. Okay. So round of applause and please welcome Dr. Vikas.
Thank you so much for the brief introduction.
So all these sessions are being telecasted on the YouTube also. So I will share link. So later on you can also
Okay, thank you so much for the brief introduction. So, as Sir has already told that I'm Dr. Vikas.
Before that, I did my PhD from IIT Guwahati, and then I did my postdoc from IIT Bombay, and sometimes I also spent at NTU Singapore. Thereafter, I have been enrolled here as a assistant professor. So just today, in the today's session, just I am going to brief you how to use the tool Abacus in order to solve the problems, whether it is related to the polymers, whether it is composite, metals, and anything else. Just basics, fundamental will be the same, and procedure will be maybe the different. And we can also ensure like there are several softwares that is dealing with the finite element methods or finite element based things. That is ANSYS is there, Abacus is there, Simulink is there. Thereafter another software SysWeld is there. So a lot of softwares is there that is handling the finite element methodology behind the screen only. It may possible that implementation procedure is different and it varies from the one software to the another software. So we will just try to brief from the basics so that you people would be able to track that, means how to use the Abacus tools and all if you are new user about it. If you are not having the any expertise or you didn't handle those things since your PhD or postdoc whatever. So how many of you are aware of the Abacus or finite element method? Okay, one guys. Any other? Okay. So SWATR means just I will move towards the interface of the Abacus, and I will start from the beginning. So how to deal with, means how to start to fabricate the product and how to implement the tool and all those things. So that will be much better. Just I will give you the brief ideas about what we can do actually by using the Abacus tools. So see, this is the one development that I did in the recent past, that is development of the model related to the additive manufacturing, whether it is for the case of polymers or whether it is in the case of composite, but it is devoted towards the metal only. So these are the procedures that I have followed during the implementation of deposition process within the Abacus. So that is firstly, since my problem was to fabricate this solution domain, that is the fabricated structure, means this is the cuboid that we have that we need to print by using the laser deposition process. Okay, so this product we have to make, okay, by using the Abacus software. So that's why we have created a firstly solution domain or a geometry kind of thing. Thereafter we have implemented the material property in order to give the behavioral aspects of the material, specific material towards this fabricated structure, that is density is there and thermal conductivity and specific heat capacity. Thereafter latent heat of fusion is there, solidus temperature and the liquidus temperature. So these are the physical properties, or we can say thermophysical property, that is playing a role if you are thinking of heat conduction equation or thermal analysis. So if we are thinking of doing thermal analysis, whether it is building process, whether it is deposition process, or whether it is temperature assisted any process, whether it is machining or something like that, since temperature is coming into the picture. So in order to model the temperature or time temperature history, just we have to do the thermal modeling. So that's why these properties, incorporation of these properties within the Abacus software is very, very important. Otherwise, they means whatever product we are going to make, that will not be able to give the specific features that will be which we expect from the in the physical phenomena or in the practical environment. So thereafter, after creating the solution domain, we have given the material properties or incorporation of several properties, thermophysical properties. Thereafter, we have implemented the thermal or mechanical boundary conditions. Since we are dealing with the thermal modeling, so there is no any requirement of the mechanical right now. Later on in the mechanical analysis, we will take care of this thing. So thereafter, we have implemented the thermal boundary condition. Thermal boundary condition in the case, there are three aspects of the heat conduction, means heat diffusion from the material. That is, one is conduction, another one is convection, and thereafter radiation is there. So all three coming into the picture if we are taking care of the temperature assisted things. So that's why if we are dealing with the melting temperature, since deposition is going on, so that's why we have to deal with that melting temperature of the material. So at that point of time, only these three mode of heat transfer will be there. That is conduction, convection and radiation, and that will come into the picture as a thermal boundary condition. So we need to incorporate these three boundary conditions. That associated equation I will show you in the later on. Okay, thereafter whatever boundary condition we are implementing, thereafter we have to deal with the thermal load. Means whatever deposition we are making, means suppose laser beam is there, or means if we are welding, then welding source is there or heat source is there. So in order to replicate those heat source, just we have to give the Gaussian heat flux, means heat load will be there. Okay, and this is in the form of double ellipsoidal. See, this is the one kind of heat source that I have incorporated during the welding or deposition process. Okay, different heat source is there, that is double ellipsoidal is there, single ellipsoidal is there, volumetric heat source is there, hourglass model is there. So depending upon your geometry, whatever you are getting during your in the experimental setup or in the experimental fabricated structure, on the basis of that you have to track or you have to select the heat source model. So on the basis of my deposition or welding process, just we got that, means by using the heat and trial method, we got that double ellipsoidal method is more predominant and can give the reliable result in the case of laser welding or laser deposition process. So that's why we went for the double ellipsoidal model. So on the basis of this, we have for incorporation of this double ellipsoidal heat source model, we have incorporated a deflux user subroutine. Subroutine in the sense that means Abacus software is there, and within that we have to generate one extra file by using the Fortran language code, because in the Abacus there is no any heat flux module is there. Okay, so if we want to migrate our heat source from one position to another position, means traveling will be there, means velocity will be there. So for the incorporation of these velocity aspects, just I have given this flux or heat source by using the subroutine only, that I will show you. So how to incorporate the subroutine and all. So Gaussian heat flux we have incorporated in order to impinge the heat source during the welding, or we can say during the deposition process. Okay, and thereafter, since we are dealing with the additive manufacturing, so element date and birth is most important, because at the position where we are giving the heat source, at that position only material is depositing. So it means that wherever heat flux will be there, just element activation will be there at that position only. So that's why we are we have also taken care of the element date and birth analysis, means the position where we need to give the laser source, there only the material deposition will happen. So on the basis of that, we have incorporated the element date and birth technique, and by using those things, whatever, since we are dealing with a lot of material deposition, see, we have to make this product, and if suppose this is of 10 into 10 into 10 mm, so, and we are depositing the layer, one layer of micrometer only, so a lot of layer will be there. So it is too hectic things to deal with a lot of layers if we are going for the manually in the Abacus. So that's why we have generated the we can say in-house develop the Python script in order to deal with a lot of layers and in a one go. So for those things, to get rid of all those things, just we have generated the Python scripted interface, and finally whatever result we can get from this model is transient temperature field. It means that transient temperature means temperature with respect to time. Means for this model, for each and every node we can get the time temperature history. Okay. So for whole the model. Now on the basis of the time temperature history, what we can actually calculate? So this GR calculation we can do on the basis of this transient temperature, which whatever output we are getting from the thermal analysis. So what is G and R? G is basically temperature gradient. Okay, this is the solidification parameters, right? So solidification parameters is very, very important if we are thinking of each and any product, right, by using the deposition process or any other things. Okay, but if we have to deal with the temperature assisted any process, just we need to take care of the GNR, means solidification parameters. That is very crucial in order to predict the microstructure as well as predict the mechanical and functional property also, whether it is tensile testing things, whether it is hardness, whether it is microstructure, metallurgical properties, any other thing. So we need to take care of the solidification parameter, and that is G and R. G is the temperature gradient and R is the solidification rate, and if we are multiplying these two factors, then we can be able to calculate the cooling rate only. Okay, solidification rate into temperature gradient, that will give you the cooling rate, and cooling rate will decide the microstructure of the material, whether it is composite or whether it is metal pure, whether it is alloy or whether it is polymer also. Means if we are thinking of the polymer based matrix, so microstructure come into existence there also. So whatever microstructure you are going to get, so that depends upon the G and R value. क्या हो गया?
थोड़ा सा बेसिक से बता दो इसको ना, ठीक है?
So just we'll go for the basics of this abacus, that would be much better. So I am opening the abacus interface finally, so that कि आप लोग थोड़ा सा miss you can get track on the basics of the abacus. So how to implement the tools and all. See, module to incorporate the heat flux and transition of the heat flux from one position to another position. So that's why we need to influx from one position to another position. So that's why we need to incorporate the deflux subroutine within that. So abacus needs to be integrated with the Visual Studio. Okay, so that's why we need to incorporate or integrate the abacus with the Visual Studio, and then Fortran compiler. Why? Because whatever deflux subroutine will write, that will be on the basis of Fortran language only. Okay, we need to write the Fortran language based deflux subroutine. So that's why Fortran compiler. So these three software is, so that's why we need these three softwares: abacus only, abacus, Visual Studio and Fortran compiler. These three things is mandatory for the modeling purpose. Okay, so this is the means interface. So see, this is first module, or we can say first tool that we have to use for the creation of the things. So see, it is asking for the name of the part, okay, and now we are going to we have to impinge the heat source over the simple plate only. So just we are going to create the plate, okay. So just I am naming it as a plate or a steel plate, whatever you want, just you can put it out as a name, okay. Since we are dealing with the 3-dimensional, so it will be 3D only, and deformable body we have to take care of, because whatever material we are going to take care of, so that will be deformable only, means since deformation will be there, and on the basis of whatever heat we are going to impinge over here. Extrusion will take care of. Now we will go for the continue. So once we will put the continue button, thereafter this type of interface will appear, and now we have to choose one origin from here, okay. Now it is asking for the enter the x and y. So since just we are taking the 25 into 25 mm plate, see abacus is not having any unitary system, okay. So whatever data we are going to feed throughout the process, so that will be considered as a one unit. It means that if you are giving input as a meter here, so throughout the material property you have to take care of in the meter only. Means whatever material property, suppose we are taking care of the density, we are taking care of the Joule setting effect, or specific heat capacity, conductivity, elongation, or so what can I say, just like another property is yield strength, thermal expansion coefficient. So all these things we need to feed as in the meter system, if we are giving the unit over here in the meter, okay. So one unit you have to follow throughout the process if we are going for the modeling in the abacus. So now I am taking care in the form of mm only, so I will give the feed like 0.025, this is in the form of meter, okay. X is 0.025, and then y is also 0.025, okay. Now done. Now it is thinking, it is asking for the depth, means whatever thickness of the material we need to provide. So just we need to give those data here. So suppose 25 into 25 was the length and width of the material. So now the thickness would be of, let's take the 2 mm or 3 mm like, so 0.003, or we can say 5 mm only. See, so this is the geometry that we have created, and it is having the specification of 25 into 25 into 3, 5, okay. Clear? Now another thing, another module, see, this is the list of module that you have to take care of sequentially only. So first is the part, and we have already created the part. Now we have to deal with the properties also, and if we need to partition it or something like that, so a lot of tools is there. So on the basis of our requirement, just we will deal with it, okay. So since we have already created one part, that is plate, over which we need to give the heat source, okay. Now we will partition it, since see this is the overall part, and the center of this one, just we will try to move the heat source from here to here. So just we need to partition it in order to make the fine meshing, means whatever meshing we are going to provide, so that will be fine over here and coarse in the outer side, because this is our area of interest. whatever heat flux we are going to impinge, that will travel from here to here, and heat affected zone will be the outermost part. So that is not our area of interest. So that's why we need to coarsen the mesh over here, and we need to we have to impose the final mesh over here, and outward direction we have to give the coarser mesh, because if suppose if we are providing the fine mesh for overall body, so it will take a lot of computational time also and cost also. So that's why whatever area of interest we are having, so on those parts we will only implement the fine mesh, and rest of the part we will impose the coarser mesh. Coarser in the sense relatively larger mesh, so that it will reduce the computational time also and computational cost also. Okay. So that's why for impinging 3 different type or non-linear or adaptive type of mesh, so we have to partition it from here to here, and another zone we need to create. So that I am going to do. See, this is a tool. See, it is already writing like partitioning cell. So we need to partition it. So that's why I am taking this one. Okay, now it is asking how do you want to specify the plane. So just we can also use different type of tool here. So let's see, using the datum. Firstly, we have to create the datum plane. Okay. See, firstly we have to create the datum plane, and on the basis of those data plane, just we will partition it. Select the plane. So this plane or this plane. Tell me, means from which plane we need to partition, means we have to create the datum plane. This one, so that means we will give the offset from here to here, and it will finally create the datum plane along this one. Clear? So that's why we are just selecting this plane. Okay. Now it is asking for the value. See, it is also asking for the flippedness, means whether we need to go for in this direction or that direction. Since material is having in this direction, so just we have to flip it up in the opposite direction. So I'll flip it like this one. Okay, clear? Since we need to partition it from here only, right? Here no material is there, so that's why we need to flip it in another side. Now it's done. Now it is asking for the offset. So since this is having the measurement of 25 mm, okay. Now we have to create the fusion zone, or we can say molten zone of suppose 2 mm only. Since we are dealing with the laser source, and laser source is having very small beam diameter, so that's why we can create the fusion zone of 2 mm only. Okay. So if for the creation of the first datum, how much it would be? At the center 12.5, 1 mm either side, and कुछ इशू है क्या? Okay, so if we are traveling from here, and 1 mm distance we have to take care of from the center. Now what will be the coordinate? 11.52. So in the meter, okay. See, first datum is created. Now the another datum from the other side. So again we need to take the same. Now again enter the value. Flipping is same, so we don't have to flip it up. Now okay, and now we have to give the 13.5. Clear? Okay. Done. Okay. Now on the basis of this datum, just we need to partition it. Now we'll go for this one, partition, and see several tool is there. Partition cell on the basis of cutting plane, on the basis of use of datum plane. Since we have already created a datum plane, so on the basis of datum plane just we will partition it. Okay. Now we are selecting this one only. Okay. Now it is asking for the select a datum plane. On the basis of datum plane, since we have selected, so first one, clear, selected. Okay, now it is asking for the create partition. Yeah, we need partition. Now it has partition. Now again another one, select the cell to the partition. See, this is the another cell, so that's why it is asking for. Now done. Thereafter again it is asking for the datum plane. So just will click it down and thereafter create. Clear? So it has been partitioned. Okay. Now very small fusion zone we have created. It's okay, just it is for the understanding purpose, so that's why it doesn't matter. Okay. Now we are having this one and it's done. Done. Okay. Now we have to move towards the another thing, that is property part. We have done with the part, we don't have to do anything else. Now in the property module, first is create material. Okay. So we need to give the material property 1400 degree, almost 14 to 1500 degree Kelvin, we can say 1200 degree Celsius almost. Okay. So beyond those and before the evaporation temperature, means evaporation temperature of the material still lies beyond the 3000 degree Celsius. Okay. So with materialistic software is there. On the basis of composition, it will give you the temperature dependent thermophysical or thermomechanical data. So if you are dealing with the composite, so just on the basis of your composition of the material, you will feed it out in the form of percentage or percentage weight. On the basis of that, it will calculate and it will give you the thermophysical property or thermomechanical property depending upon the temperature. GMAT Pro is there. One software, this one. Another software is also there. Okay. So since my material is not having the tendency of the heat generation by itself, so that's why we don't have to deal with the heat generation, and Joule's heat impacts we don't have to, just we have to give the latent heat. Latent heat of fusion is very much required, because if we are dealing with the solidus and liquidus temperature, so within those latent heat of fusion may work. So that's why we have to give the latent heat. So 2400 just I am giving. What is the solidus temperature? Solidus temperature, if we are talking about the steel, then almost 1400 Kelvin. Okay. Now liquidus, what is liquidus temperature? Liquidus temperature is melting temperature. Okay. So range is suppose 1450. So the means most probably or most significantly means the range of solidus and liquidus temperature is varies between the 50 degree. Okay. So if it is cellular temperature 1400, then we can take it melting temperature as the 1450. It is also available in the literature also. Okay. So you can get it from the literature. Now another property, specific heat capacity, that we have already discussed in first slide. So specific heat capacity 250. All this data in the form of SI unit only. Okay. So these are the four very important property that we need to feed if we are going for the thermal modeling. Clear? So whatever property we have already incorporated, that is also visible in the form of list here. See, density, firstly we have fed it, and thereafter conductivity, then latent heat, and then specific heat capacity. So this is the most significant and important property that deals with the thermophysical property or thermal analysis within the model. So that we have already fed it. Okay. So now from the perspective of the material property, we are done. Now we will put OK here, and if you are having the temperature dependent property available with you, just you can feed it there in the material module. Okay. Now the second, this is the Now property module is clear. This one create material. Everything is understandable. Okay, clear. Now moving to us. Now this is the second one, create section. Since we have created the property module only, but till now we didn't incorporate those property into our material, our product or our parts. So just we have to import it there. So that's why we need to create the section. So we'll create the section. Only one section means since same material is there, we are dealing with the similar material. So that's why we need to give the section 1 only. And homogeneous, throughout the material homogeneous property we need to provide. If you are dealing with the composite, then we need, you have to give the different materials properties. It is also available over here. Huh? Okay, now this is the material. Means material property. In the material property module, just we have created the steel named property module. Okay, so that's why it is showing like this one. You have already created the material steel. Okay, in order to fit the material property over here. So that's why we have to take care of this one. Now it's done, section created, and that is in the form of steel only. Now the third one is assign the section. Now section has been created, material property module has been created, part had been created. Now on the created part we have to import those section along with the material property. So that's why it is asking the assign the section. Okay, assign the section since all material is having same property. So that's why we'll select whole property, whole material. Now it's done. Okay, see section 1 we have already created. Section 1 we have created. Okay, so now we have to import it. Sorry, now done. See, after the incorporation of those properties or those material properties, it has changed the color. Now it is in the form of steel only. Okay, now it's done. Now we don't have to do anything with this module. Property module is over. Okay, now assembly. Since we are having only one simple structure, so we don't need assembly and all, just we have to go through this module only. See here it is asking about the dependent or independent mesh. Okay, so since see this is the global coordinate system. Okay, and whatever on the basis of this assembly has been created, that is local coordinate system. Okay, suppose if you are if we have to impeach the laser source over here. Okay, so and the local coordinate system is here only. It means that laser source, if we need to put the laser source here, then in the subroutine section, whatever we are dealing with in the Fortran language, so in the subroutine, so what we need to do, we have to give the specification of this one or this one. Means coordinate we need to shift from here to here. Are you getting or not? Means suppose if local coordinate system, see this is the first idea. Now the second idea, just I will transform the coordinate system so that you would be able to track it out. See, now we are changing the place of the local coordinate system. First one, now what happened? See, what happened? See, local coordinate system shifted towards this end only, at the center of the plate. Okay, so now if we'll write the subroutine, then we don't have to give the specification of this one only, because local coordinate system is already shifted over here. So we'll start from the 0, 0. Are you getting or not? If coordinate system will be, if the local coordinate system will be like previous one, suppose here means at this position, so we need to give the extra specification of this coordinate, and thereafter finally we have to travel from here to here. And now this time we don't have to take care of the this position, just it is already shifted over here, and we need to take care of only this position, and we need to run the heat flux from here to here. So it will, we have to give the coordinate from 0 to 0 only. Okay. So on the basis of your requirement, just you can place your local coordinate system. See, if you are not getting something, then please ask. Okay. Once it will be clarified, thereafter I will move towards the another step. Okay. So now assembly is done. We don't have to do anything else in the assembly, just we have to put the local coordinate system in the assembly model, nothing else. Okay. So we have already created and we have already given the local coordinate system over here, and now we have to run the heat flux from start to end position in order to deposit the material either, or in order to weld the material. Okay. Whether it is plastic, polymers or composite, whatever you want, just you on the basis of material property module it will be decided. What?
Shifting of coordinate system. Is it mandatory?
No, it is not mandatory. No. Yeah. Exactly. On the basis of suppose at the initial position, if you are not having the local coordinate system here, previously it was here. Yeah. Those things you can do it. Just you have to change the things in the subroutine then. Okay. Now step module is there. It is very important module actually. So first one is in the step module. First one step is, since we have to go for the heat transfer model, if we are going for the thermal modeling. So heat transfer things we need to select. Otherwise, if we are dealing with the mechanical analysis, or we can say stress analysis or distortion analysis, then in that stage you have to select the static and general. Okay, static analysis. So now since right now we are dealing with the heat transfer model, or we can say thermal modeling only, so we have to go for the heat transfer and thereafter continue. Okay. Now it is asking about the transient behavior time period, means whatever will be the total time of the welding or deposition, it is asking for those things. So suppose our specification was of 25 into 25 into 5. Okay. So length, just we are dealing with the length only. So what would be the time? Suppose 10 mm per second we are giving as a speed or velocity of the laser source. So what will be the time? Means 25 mm and 10 mm per second we can take, then 2.5. Okay. 2.5 time is there in the form of second. But see, actually if we are dealing with the thermal analysis or thermal modeling, so this is the welding time or deposition time. Along with those time we also have to give the cooling time in order to take our substrate up to the room temperature, because immediate after the welding it will not be at the room temperature. So that's why we need to add some extra time in order to provide the cooling phenomena also. Okay. So since it is for the welding or deposition purpose is taking only 2.5 second, now we need to add the 10 to 15 or 20 second extra in order to provide the cooling rate, so that whatever curve we will get on the basis of thermal modeling, it will be full up, just it will rise up and therefore again it will cool down up to the room temperature, and that is the more beneficial for us, because in the practical environment or physical phenomena, what is going on? Just rising the temperature, we are doing the welding, and again just we are leaving those material up to the room temperature, thereafter we are going for the commercial application and all. So that's why we need to feed it out some extra time depending upon your materials only or their conductivity. If suppose some material is having higher conductivity, means diffusion rate, heat diffusion rate is very high for those material, you can give the less amount of the time, cooling time. If you are having, suppose if you are dealing with the titanium whose specific heat capacity or thermal conductivity is less than that of steel, then it means that thermal accumulation means thermal energy accumulation tendency of the material is very high. So in that case we have to give the higher amount of the cooling time, right. So there you can also twice the time like this one. So here I am giving the 10 second extra for the cooling time. Okay. In this module 3 things is there. See, in the basic module just it is asking for the total time. Now we have to go for the incrementation also and others also. Just we'll let it, we'll think. Okay. There are two type of stages is there. Since we are dealing with the transient in the sense what? Transient means what? With respect to time, isn't it? So since we need the data with respect to time only, so that's why we are going for the transient heat transfer analysis. And on the basis of what? Which theory? On the basis of which theory we are going for this analysis? Fourier heat transfer. Have you heard of this Fourier heat transfer analysis? So Fourier based heat conduction equation we are incorporating in order to do the thermal modeling. Okay. Fourier based heat transfer analysis we are doing, and that is transient in nature. Okay. Now in the incrementation, in the same module, if we are going for the incrementation, see whatever things is there, it is asking for the either automatic or fixed. Okay. So in the automatic, it is giving some flexibility to feed it out some extra things. So that is maximum number of increment is there, increment size it is asking for, minimum and maximum is there. So for providing the flexibility in the fabricated part, just we need to feed it out. Initial in the sense, suppose our geometry is very complex, okay, and it is having a lot of number of elements is there. So it whatever iteration is there behind the screen, so that is based on the Gaussian model, Gaussian based analysis is going on, or trapezoidal also on the basis of we can say numerical method. So initially it will iterate up to the 17 stage abacus. Okay. So if it will not compile, means whatever input data you are giving, if it will not be compilable for the abacus, then it will abort the simulation. So for avoiding those circumstances, thus we are giving to give the initial stage. Initial in the sense कि iteration के stages means whatever will be the size of iterations, each iteration. So that we can give suppose 0.001. Okay, initially we are giving. Okay. Now it is asking for the minimum, means minimum should be less than that of initial also. Suppose it will not iterate by taking the size of 0.001, then it will decrease the size of simulation or iteration. Okay. So for those things just we need to give the less 0.00001. Okay. Minimum we have given, means if it will not compile by using these steps, means 0.001, then it will go towards the lesser stage in order to make the simulation or in order to run the simulation. Okay. So that's why we need to provide the minimum less than that of initial one. Okay. Now maximum, if your model and input is very effective, then you can give the one. So what will be the effect of these three things over the simulation? Means if suppose in initial stage it is taking during the simulation, so it may possible that 12.5 second our total time is there. Okay, and initial step will be this one. Then what will be the maximum number of iteration? 12.5 into, means this is the one step. So how it will complete 12.5 second? Means 12.5 divided by 0.0001, then maximum number of increment will we would be able to calculate. Are you getting or not? Marker is there. See, total time of welding is 12.5, okay, and thereafter initial increment we are giving for the simulation, that is 0.001. Clear? So what would be the maximum number of iteration? 12.5 divided by 0.001. So ultimately it will give okay 12,500. Clear? So this would be the maximum iteration. Clear? If it will give, it means it will take, if simulation, our model will take the initial step like this one. Suppose iteration is not going completely favorable in the condition of initial, then it will go for the simulation will go for the minimum. That's why we are giving the minimum stage. Okay. Now it will move towards the 0.0001. Clear? Now on the basis of this one, maximum increment what would be? Whatever 12.5 lakh or something like, okay, this would be okay. So this would be the maximum increment. Now on the basis of maximum increment size 1, this is 1, we did put 1 here maximum. If your model is appropriate, everything whatever material property you have incorporated, that is significant. Okay. Now it can run over the maximum size of 1. Then what would be the maximum increment size? Maximum increment number 12.5 only. Okay. Because simulation is going on in the one step in 1 second only. So it will complete in the 12.5 second. So what is the difference between this one and this one? Computational time is varying. Okay. Simulation time is varying. So if our fabricated model is not appropriate, it means that it is taking the minimum amount of time, minimum amount of stages or steps, then it will take the maximum amount of time. Clear? So that's what we have to deal with in the step module. So that's why it is giving the flexibility like this one. Okay. So this is the significance actually in this module. Okay. So now 100 is fine here, 100 is fine here. No man, how it is fine? Because maximum number of increment on the basis of minimum is more than this one, no? Right, it should be more than that on this one. Means whatever 1.25 lakh, then if you are giving the 10 lakh only, so it's okay, no problem. Because our simulation time is 1.2 lakh, no? Thereafter it will finish the simulation. It will not go beyond those things. So maximum time whatever you are going to take during the simulation on the basis of whatever feeded, means whatever value you have feeded, that will be okay. Okay. So whatever maximum amount of time or maximum number of increment you are expecting on the basis of these data, that you have to feed it here. Clear? If you will put 100 there, then irrespective of these data, it will abort after 100 steps. So it will not go beyond the 100 step there during the simulation. It means simulation will be aborted towards the few steps only, like 100 steps. Okay. So that is the significance of this one. Now it is asking for the maximum allowable temperature change per increment. Means what you want, means after 1 increment or after 10 increment, actually it is asking for the 1 increment only. So after 1 increment, how you are means how much temperature change you are expecting. Means suppose after 1 increment, whether it will be of 10 Kelvin or 10 degrees Celsius or 100 degrees Celsius, depending upon your material, you can feed it out here. Okay. So max to max you can give. If simulation will tell them on the basis of calculation on behind the screen, if it will be less than that of 100, that is also okay. What? Source? Okay, source of this value. Actually, it will come on the basis of your experience, whatever literature review you will get it on. Means in the literatures you will get means how much temperature change you are expecting within means for the single increment and all. Maximum allowable emissivity, that is also on the basis of literature data, that is fine. Now another thing is other only. Okay, so if we will go for the other is nothing. If we will go for the fixed one, so see in the fixed one it is asking for the only increment size, means they are not providing the flexibility of giving the feed of initial or minimum or maximum value, right. So if you are comfortable or you are having confidence that your model is very appropriate, you do not have to give the flexibility of minimum or maximum, then you can go for the this one increment size. But if some complexity will be there in your model and it will not simulate on the basis of this fixed size, then it will abort. So it's better we will go for the automated system, no? It's better we need to feed it out. If some complexity will be there within the simulation, then it will take care of, Abacus will take care of on the basis of PD data. Okay. Now it's done. Now step module is done. Okay, since we are dealing with the this second things, actually if we are going for the field output, it is actually field output. See, field output means what? Field output means what? Whatever result you are expecting, what field you need as a output, that it is asking for, and we need what? We need temperature, time temperature history only. So we can go for here. You can continue it, and it is asking for the here. See, in the list it is given, and you can mark it up what you want. Just thermal only, and in the thermal just we need heat flux, nodal. NT actually represent the nodal temperature. Okay, and nothing else we need. Heat flux you can also go for. See, just you have to delete it up. Resultant flux you can expect this by using this model. Heat flux, see these three field output you can expect on the basis of this model, that is nodal temperature NT, and heat flux HFL, and resultant heat flux in the different direction. Okay. So these three things you can opt. Now it's done. History output is not required here. This one. Now interaction. Interaction, you have to just follow the sequence of the model. You don't have to take the pain, means what we need to feed and all. Just you go for here in this model tree, and you can opt the sequentially, like firstly you create the part, thereafter you feed the properties, then you go for the assembly module, then step, then interaction, then load, then mesh. And since we don't require the optimization for this model, so we don't have to deal with this one. Now we will go for the job submission. So sequentially you have to go for these things. Now step is done, now interaction is there. Okay. So in the interaction, what it is asking for actually, so whatever heat transfer we are going to create on the basis of this thermal model, so that we need to feed over here, means conduction, heat transfer mode is there. Okay, whatever boundary condition we have already discussed. So in the thermal boundary condition, just we have to deal with the three mode of heat transfer, that is conduction, convection, radiation. And conduction, for the purpose of conduction we have already incorporated what? Conductivity. In the material property we have already given that thermal conductivity, right? So that will take care of conduction. Now we need to feed the convection and radiation. So that's what we need to give. So surface film condition means that convection it is asking for. Okay, now we'll continue. It is asking for the surface from where you need to feed the data. Okay, so since you can also opt these three, because see whatever convection is there, that will also depend upon the temperature. Okay. So since in the fusion zone there will the chances of getting higher temperature is higher, because heat flux will travel from here to here, right. So it will have the temperature really means corresponding to the melting only. Okay. And it is having the higher, very much high temperature rather than this area and this area. Okay. So now on the basis of temperature dependency we can also create the surface film. So just will select this one, and by pressing the shift we can also select more number of surface at a one go only. Okay. Now again this one on the bottom side. This one. Okay. Now the fusion zone completed. Fusion zone done. Okay. Okay, now we need to press done, and then it is asking for the value we need to give. Okay. Now for the sake of example, just I am giving the data 25. Okay. And we don't have to do anything else. Sink temperature is asking for. So sink temperature means what? The temperature at which we are going to start the building or deposition. Clear? So what is that? This is room temperature only. Okay. So what is that? How much value we need to give, since we are dealing with the SI unit, and that is Kelvin only. So that's why 300 only. That's done. It is already important. Now again we have to give the surface means convection for the another part. This one and this one is already remained. Okay. And some value we also have to give, since convection and radiation always occurs in every temperatures. Okay. So we need to give the data for some, means suppose it will have the 1800 degree Celsius, then at least it will have the 1000 degree or 1200 degree, because it is intact surface. So that's why some temperature diffusion will always be there. So we need to give some data for this one also. Okay. Now I'll select the surface, whole surface, since we are dealing with the both material. And if you are dealing with the dissimilar material, suppose, so what you have to give, means you have to create the another section of this one, means two section we need to create. That is for the suppose steel alloy is there and titanium alloy is there. So you need to partition it from the center, and thereafter you have to create the two section and two module of the material property, and you have to feed the different material property for the different alloy, and now it will be treated as a dissimilar material. Okay. Now right now we are taking care of the similar material only. Okay, that's done. Since we are dealing with the similar material, so we can also select here also. You have to select each and every surface. Okay. Now apart from the fusion zone, everyone is selected over here, I think. Okay. Now it's done. Now it's done. Done. Now it is again asking for this one. So since with respect to, if we are talking about the higher temperature, so with respect to higher temperature, convection is convective heat transfer coefficient is having some dependency or not. Just we check it out. Just I am feeding it here at 23. With respect to medium, it is actually vary. With respect to water or air, something like, isn't it? Okay. Now it is, we are feeding 300. Now it's done. Okay. Now we have already incorporated the thermal convection heat transfer. Now we have to go for the radiation, and it is given here, surface radiation. Clear? And surface radiation we will talk. So surface radiation is very effective if we are dealing with the higher temperature, because it is having the magnitude of radiation, how much? 10 to the power 4, right? Sigma epsilon to the power 4 means sigma epsilon t naught minus t to the power 4 as something. Okay. So it means that at a higher temperature, if we are increasing or elevating the temperature, so it will have the greater magnitude of emissivity, or we can say radiation heat transfer coefficient. So for those sake, just we need to feed the emissivity for the fusion zone, which is having the higher magnitude at a higher temperature. Only fusion zone I am giving. You can also give the other parts as well, because radiation always happen at every temperature, but magnitude will be very less. You can also give those things. I think it's done. Okay. It's done. Radiation. Now again it is asking for the emissivity. It is asking for. Why it is having a lot of time? Okay. Now emissivity, it must be less than 1. Okay. So for the case of steel, 0.6 is more than sufficient. I think 0.5, it will vary from the 0.5 to 0.6 or 6.7. Ambient temperature will be the room temperature only. 300. Now it's done. Okay. Now we don't have to do anything else in the interaction module, since we are dealing with the thermal model. Now it's done for the interaction module. Now again for the load. Okay. Whatever load we are, what load we are going to give for the thermal model? Temperature only, heat only. Right. So create load. Okay. Now there is a two mode actually. This is surface heat flux and body heat flux. So what is the difference between the surface and body heat flux? Actually, if we are having the material, very thin material, if we are dealing with, so it means that it is not having the thickness. So we don't have to take care of the body, just thin surface, and surface heat flux would be okay. Okay. Now if we are going for the thickened material, just we are having the 3 mm thickness material, we have to take care of the heat diffusion from here to here on also. So throughout the thickness. So that's why we have to go for the body heat flux only. And in this case, if we will go for the surface heat flux, then whatever heat flux will impose over the surface, that will entrap only over the surface only. Its effect will not be diffused throughout the thickness. Okay. So that would be the discrepancy that we will get if we are going for the thickened material and we are incorporating the surface heat flux. So we need to take care of those. See, it is asking for the select the body for the load. See, select the body for the load. So load where we have to import, since heat flux will be here only, so in this zone only. So that's why we have created the partitioned section in the initial stage. Now you can correlate with those things. Otherwise it will select whole the surface, and that is not mandatory if we are dealing with the laser source. So that's why we need to go for the partitioned section only, and now done. And it is asking for the uniform, yeah, uniform in this zone, whatever selection we have made in this zone, uniform distribution of the heat load we need. So that's why it uniform we need to give, and magnitude it is asking for. So magnitude we need to put 1 if we are providing the subroutine that is user defined. Once you will put the user defined tag over here, it will write here user subroutine deflux must be attached for the analysis job. Whatever we have already discussed, that we have to give the Fortran based deflux subroutine. Clear? So that's why if we are giving the magnitude of 1, so whatever magnitude will be incorporated in the subroutine, that will take care from there only. Whatever power will give, velocity will give, on the basis of those value it will calculate the magnitude, and finally it will multiply with the 1 magnitude here, and thereafter it will increase over here. Clear? It will give the 2 magnitude over here, and power velocity will be different here there. Whatever will be the calculation. See, heat input if you are studies. So heat input basically HI is equal to power by velocity only. Okay. So if power will be the 1000 watt and velocity hour is 10 mm per second. Okay, now 100 joule per mm. This will be the heat input. So on the basis of that, heat flux will be calculated within the. Now it's done.
When will this magnitude thing come into picture? Multiple variables.
Oh, that I didn't use these magnitude things, but I'll dig it out, thereafter I'll let you know. So where it can be, like, I think internal heat generation condition will be the one circumstances in which magnitude come into the picture. I'm not so sure about it, just I'll dig it out, thereafter I'll let you know. Okay. Now nothing we need to do extra in the load module. This is done because we have to deal with the laser load, and that we have already incorporated, and the boundary condition we have already given in the form of thermal things, that is conduction, convection, radiation. We do not have to take care of the other boundary condition, that is mechanical boundary condition and all. If we will deal with the mechanical model, then we will go for the these things, creating boundary condition and all. Okay. Now we have to go for the important module, that is mesh. Okay. So since now mesh is coming into the picture, okay. See, so whatever procedure I follow for the meshing, so that is a little bit hectic, but it is giving the surety of the things. See, firstly we need to go for the seed module. Okay, seed module at the top, and we need to select over the. Okay. See, in the left side, it is also whatever material we are going, we have already given the input. So that is also created in the tree module over here. See, this is the first one part, that one part we have created, one module property we have created, thereafter one section we have created, everything is also visible over here. Thereafter instances on the basis of this part, this is instances is there, sets, features, means whatever features we have incorporated, that you can visualize all those things over here by clicking over here, like set and all, sections, parts, material, steel plate, whatever we have created on the basis of that. Okay. Now we'll go for the assembly and we'll made it independent. so that will import the means will give the impose the finer mist or coarser mist both. So I'll give this thing. Let's see from where we can go here. Make independent. Okay. Now we made the independent, so that means fine mesh will be implemented over here and coarse mesh here. So that's why independency is mandatory. Okay. Now we'll go for the seed in the that model, mesh model. Okay. Seed instances. We don't have to change the global size. Just we need to give the we don't have to change this one. This size is appropriate. If you want to change the global size, you can change, but this is more than enough. Now we'll go for the seed again and ages. Okay. Now firstly we'll mesh the fusion zone, finer mesh. So we need to select each and every edge in order to make the fusion zone very finer. And if you want to use the abacus, I can also provide the videos as well as crack version of this abacus. Okay. So once session will be done, you can also contact me if you are interested in using those. Okay. Now I think this fusion zone is done, I think. Okay, these two remain. Done. Now this is selected. Okay, fusion zone is selected. Oh, it's done. Okay. Now it is asking for the approximate element size. So actually whatever measurement I have taken, actually this is the hit and trial method. Whatever element size you will provide, firstly you have to go for the mesh sensitivity analysis by taking the different mesh size, and any other parameters you have to keep the constant value, and thereafter you have to go for the validation with the literature whether the appropriate result you are getting or not. So on the basis of that you have to make the selection of the element size. But what I prefer is 1/10 of the means whatever measurement we have taken from this one only. Okay. So 25 we have taken. So 1/10, it means that what is the 0.25, 2.5. No, actually it is in meter, no? 2.5. So 10 extra we need to put. Okay. Now 2.5 I am taking. See, this is fragmentation is done in the fusion zone. Okay. Now we have to go for the outer part, that is coarsen mesh. So seed again age. Thereafter we have to just we will frame it so that every age will be visible. We don't have to we don't require the movement and all. Okay. By pressing the shift you can control whole, means you can make the selection for the whole geometry. Okay. Done. Now it's done. Done, and thereafter now again it is asking for the element size. So we'll take the 25, means 25 is I think very much larger size. Just okay. So just I have taken 2.5 mm element size for the coarser mesh. Clear? Because unnecessary it will increase the computational time and cost also. So that's, and this is not our area of interest so much because heat diffusion will be less. In the case of laser source, heat affected zone will be very less. Okay, if we are going for the laser source, laser beam source, so that's why it will not, temperature will not go beyond the 2 mm or 3 mm. So that's why we need to avoid it. Now it's done. This done. Okay. Now seed is done. Instance and age, that is more than sufficient. Now in the mesh we need to go for the control. It is asking for the selection of the region, whole region. So that's why I have selected. Okay. Now structure or sweep basically means I used to implement the sweep on the basis of whatever heat and trial and optimization I have made for my PhD thesis or postdoctoral work and all. So on the basis of that, just I am saying that I used to use sweep only. Okay, and hexagonal mesh size. So it's done. So again in the mesh control is over. Now we don't have to go for the orientation. Element type is very important things. Again it is asking for the select the region to be assigned element type over here. Okay, so that's why I selected here, and then done. Now it is asking for C. Now it is asking for what kind of element size you have to take care of. So since we are dealing with the thermal model, so we have to go for the heat transfer element. See here the list is there and the heat transfer is there. Okay, we don't have to change all those things. Just see, if you are going for the heat transfer element, see whatever will be the node or whatever will be the element size that is represented over here, that is DC3, D8. You might be heard of this name in the literatures and all if you will go for the literature based on the simulation. So 8 noded linear heat transfer break element it is incorporating on the basis of whatever sweep and hexagonal mesh we have used. Now it's done. Now we have to implement the instances. It is asking for the mesh. Now it's done. Now it will give the mesh. We have to go for the again we need to see this one with the age. Okay, no, for the fusion zone again we'll select thing. See again we are placing the age. Not done. Okay. 0 to 5. That is more than sufficient. Now again we need to put this one since we have already deleted the mesh. Okay. Now it's done. Element type done. Now put the instances. Yes. See. See the mesh once. See, in the fusion zone it is very fine mesh, and outer ward it is different type of quotient mesh. Okay, because this is our area of interest, and we need to take care of each and every elements of the fusion zone. So that's why we have given the final mesh over the fusion zone, and in the apart region it is coarser. Okay, now you can visualize this one from any area like this one. See. Okay. Now meshing is done. Everything is already done. Now we don't have to go for the optimization. Now we have to finally submit the job. Okay. So job name is steel plate, you can write plate, and space is not allowed here, so that's why. Okay. Now in the submission module it is asking for nothing, just we have to go for the general, since we have to incorporate the deflux subroutine, okay, for which we have already given in the load module that we are going to import deflux subroutine. Okay, so that's why it is asking for the user subroutine file here. Now we have to browse it here. Okay, if we will have something, right now I don't know means whether it is having something we have. I don't think means we have to also change the subroutine means depending upon this model. So that will be another part. I don't think means I would be able to cover it. So just we need to browse the subroutine and thereafter finally we have to okay, see, now it is created, it is steep plate model that we have created and the status is no. Now we have to check the data check, the model attribute absolute zero temperature. Okay, another thing we need to take here, see in the model part, the first, second one, top second one menu bar, we have to give the attribute means edit attribute model. See whatever data we have already given for the sake of heat transfer. So how it will calculate the heat transfer coefficient or heat transfer depending upon the convection and radiation. So for that we need to feed the Stephen Boltzmann constant 5 into 6 7 into 10 to the power 34 minus 34 whatever, okay, and absolute zero temperature we also have to feed it out. So that's why it has asked for those things. So absolute zero on the basis of the Kelvin, what value we need to feed? Absolute zero temperature is 0 only in the form of Kelvin, right? You will go for that Celsius, then it will be minus 273. Right? Stephen Boltzmann constant now we have to feed 5.67 into into 10 to the power minus minus 34, right? Minus 8, okay. So whatever data is there, just you can put it out here, okay, minus or something like whatever. Okay. Now again we'll check the data. If something will be missing, then it will let us know that you didn't feed this one. So history output is not required because we have already given the field output as a nodal time temperature. Okay. Now we need to yes, and we'll submit the job. Then it will run the simulation and will get the results. Since we have not incorporated the subroutine deflux, so that's why it will not calculate. Okay. Now this is the overall procedure for the case of thermal model calculation. I don't think it will give the data because we have not incorporated the least ordered or something like that error it is giving because we have not incorporated the deflux subroutine. So whatever result on the basis of that we got, so that I am showing you from here. See similar kind of things I did for the titanium alloy, and these are the data. See governing equation, whatever governing equation it is following, abacus is following for the calculation of the nodal time temperature, so that one. Okay, and this is the thermal 3-dimensional because our plate is of 3D, so that's why conductivity is K and x, y, z is the Cartesian coordinate system in the different direction. This is the heat flux which we are importing, okay, and this one is the density of the material which we have already fed it in the material property module. This is the specific heat capacity, this is the temperature gradient, and this is the velocity that we need to feed by using deflux subroutine, okay, and this is the heat flux that we need to give in the form of double ellipsoidal. It will also be incorporated within the subroutine only. For the subroutine I will take another session so that you would be able to get it, how to write the subroutine and what it represents actually and how it will be incorporated with the abacus. Okay, so one session will be devoted towards those things. I don't know if on the basis of availability of those sessions, just you would be able to integrate both things. Okay, so this is a power density that we are going to give in the form of the double ellipsoidal, and these are the optimized parameters. And what is this parameter actually? See, I am showing you. See, this is the actual welding, means welded or deposition material. Okay, this one. This is the experimental result and this is the simulated result. So on the basis of thermal model that we have already done. So on the basis of that, it is giving that the higher temperature over here, and this is giving the deposited material, or we can say the heat of fusion zone. Okay, this is the welded zone. Okay, and now I validated this with the this experimental, and associated temperature is visible over here, and this is in the form of Kelvin only, and it is showing the 2324 Kelvin. It means that 200 degrees Celsius as a maximum temperature it has given, that is beyond the melting temperature of the material and less than that of evaporation temperature of the material. Okay, and associated temperature distribution is this one. Time temperature history we have calculated on the basis of this. Just you have to select one node from here, and thereafter it will give the temperature like this one. Temperature profile means at the room temperature, it is, since we have started with the 300 degree Kelvin. Okay, so this is the contour temperature contour plot that we got from the thermal model, and we have validated this with the experimental result. This is the fusion zone, and this is the heat affected zone, that is similarly showing over here almost. Okay, some percentage of error is there since whatever assumptions we have made. So on the basis of that, we are getting the some type of errors. Okay, and this is the associated temperature distribution that we have initiated our simulation with the at the room temperature, that is 300 Kelvin. Now it is rising up and it is giving the higher temperature. It is actually somewhat towards the base material side, so that's why it is giving a temperature 1200 degree only. But however, this zone's maximum temperature is visible over here, that is 2000 degree Kelvin, 2000 degrees Celsius, that is 2300 degrees Kelvin. Okay, so these are the results, and these are the another part, that is mechanical analysis. On the basis of this thermal part, that whatever result we got from the thermal modeling, we have incorporated those results for the mechanical model, and on the basis of that we got the result for the dissimilar material it is showing. So that is the another part that also in the different, say whatever assumptions we have made, that is given over here, and this is the plate that I have already simulated on the basis of those analysis which we have discussed over here. Okay, this is the final mesh we have implemented, and this is the very thin plate that we dealt with. So these are the data. A lot of things I did on the basis of this simulation and all. See, this is the distortion and residual stress, means just whatever we have discussed, that is on the basis of thermal model only, and whatever result we will get from the thermal model, that will be incorporated as an input for the mechanical model. So whatever model we have created, just we need to change 5 things for mechanical modeling. That is, first is material property, since we have given only thermophysical property for the thermal model, but if we are going for the mechanical model, then we need to incorporate the mechanical properties as well. So for the sake of incorporation of the mechanical property, what we need to give as a feed, that is thermal expansion, temperature dependent thermal expansion coefficient. Another properties, yield strength, means whatever strength will be there, like this one. See, this is the material properties. So for the incorporation of the elastic zone, just we have to give the data related to elastic modulus, okay, Poisson's ratio. So that will take care of this part. Again, for the incorporation of mechanical property, for this part, what we need to give? Plastic property, and different theory is there for the plasticity incorporation. That is, Rios model is there, von Mises based model is there, another different model is there. So on the basis of that, you have to incorporate the plasticity property. So what I am incorporating, that is associated with the von Mises. For the sake of those incorporation, I need to feed the yield strength versus plastic strength. Means yield strength in a sense, suppose you have to incorporate this data, so corresponding yield strength from here and corresponding plastic strength from here. Okay, so this experimental data, just we can extract from the experimental things, and thereafter we can incorporate in the plasticity model in the this one. Okay, so for the sake of mechanical property incorporation, so elasticity property, plasticity property, thermal expansion, these things we have to incorporate for the mechanical analysis. So one thing that we need to change is the property module. Now the another thing we need to change is mechanical boundary condition. Okay, this is the second thing. Third thing we need to change is step module, where we have given only 3 heat transfer things, but we need to go for the static general analysis if we are thinking of the mechanical. These 3 things is there. 4 things what? 4 things is element type. Element type, there also we have given the data related to the heat transfer only. Element type. Okay, now we have to go for the stress, 3D stress. I'll show you. See here, step module. No, not here. Step module interaction. This module. Here. So we will go for the element type, just for the sake of understanding I am saying. See, here we have selected the heat transfer, but we need to go for the 3D stress, that is the first one. Okay. So this is the third thing. First is the material property, second thing is mechanical boundary condition, third thing is element type, fourth thing is step also. Okay. 3D general means this is the element type, step I will also show so that you will get it. See, this is the step. Okay, step 2. It is not asking for the step actually. So I will create this. Delete. See, here we have used heat transfer, but we need to go for the static general. Okay, clear? So whatever change we have to make is material property, then mechanical boundary condition, then step, thereafter element type, 4 things. Fifth thing is whatever data we will get from the thermal modeling, time temperature history, that we have to in the form of ODB file, .odb, that will be generated on the basis of thermal model, that we have to import over this module in the interaction, I think. This is a boundary condition, mechanical boundary condition. Okay, we have not created those static general modules, so that's why it is not taking. In the load module here, we need to feed the time temperature history. Finally, we have to submit the job. Okay, on the basis of that, we can be able to do the thermomechanical model. So finally, we can get the result like this one that I showed in the PPT, like this one. This is the distortion, this is the stress distribution that for the different boundary condition it is given over here. Okay, and on the basis of that we can solve it. So these are the things that we can solve by using the 5pm, because many times we don't have the facility, we are having the constraint about the physical facility or experimental things which cannot be tracked by using only the which can be only tracked by the sophisticated setup that we don't have actually a lot of time. So on those things, for the sake of those resolution, just we can go for the simulation things and finite element modeling tools and all. Suppose if we are going for the real time trackment of the residual stress, something like, or thermal stress, whatever thermal stress is generated during the deposition or during the welding of the plastic polymer or whatever composite is there. Okay. So, real time management, or we can say in situ trackment is very difficult. Okay. In situ tracking is very difficult. So, on those things, means for the replacement of those things, just you can go for the FAFE tools, so that you can be able to visualize what is going on within the material by incorporating all those physical phenomena. A lot of things, or a lot of constant we are making, or boundary condition we are making. Suppose here whatever we are talking about the thermomechanical model. So, in that case, just we are taking care of the thermal, and thereafter on the basis of that thermal load we are generating the mechanical behavior. So, that is not the prominent thing, because we are skipping the major thing, that is metallurgical aspect, right. So, metallurgical aspects we are not incorporating. It means that we are lacking very important things. Means on the basis of this thermal model, or on the basis of the temperature agitation of the over the material, microstructure will be changed, solidification behavior will be changed, and thereafter finally it will impact over the mechanical properties or functional property at the end. So, we can't do these things. We have to incorporate all those phenomena as well in order to get the reliable model, so that it will be useful for the commercial purpose and at anywhere. So, for those things, for the for resolution of those things, just I incorporated metallurgical model during my PhD at IIT Guwahati. Okay. And just I generated these. What I did actually, on the basis of this flux model, I have calculated a temperature distribution, and thereafter on the basis of this temperature distribution, just I calculated the cooling rate. So, whatever cooling rate we are estimating, or whatever heating rate we are estimating, because whatever phase transformation is going on, that is either in the heating cycle or the cooling cycle within the range of temperature. Suppose if we are dealing with the steel alloy, so 700 to 1000 degrees Celsius, it is giving the phase transformation, ferrite to austenite to ferrite, or ferrite to austenite, whatever things is there. Okay. For the sake of titanium alloy, it is giving the alpha to beta transformation, or beta to alpha, or martensitic transformation. So, within the range of temperature it is giving the phase transformation. So, that is why what I did, on the basis of the temperature distribution, just I calculated the heating and cooling rate, and thereafter finally by using this cooling diagram, means CCT diagram, or time temperature, or transformation diagram, just I calculated the phase fraction of the phase transformation during the heating cycle or the cooling cycle, and finally we have incorporated for the calculation of the residual stress. So, these phase transformation phenomena ultimately impacting the residual stress generation or formation within the material. So, just I resolve this kind of problem for 3 material, that is steel alloy, and P91 stainless steel, and P91 steel, carbon steel is there, and one titanium alloy. So, these 3 material, for the sake of these 3 material, I developed the thermo-metallurgical mechanical model in order to incorporate the metallurgy as well. So, finally I calculated the temperature, thereafter phase fraction, thereafter associated strain which is going into the which is coming into the picture in the material, and finally we have calculated the residual stress. Residual stress is the very important phenomena, as we already know that, and if we are talking about the composite, it is also huge factor, means it is a very predominant factor that we need to take care of, because in the composite what we are dealing with, different material, different composition is there. So, different material is having different expansion and contraction phenomena. So, on the basis of this complexity or misalignment, we can say a lot of generation of residual stress is possible, means a lot of chances is there that we can get the huge amount of the residual stress. So, for those things, for the sake of resolution of this problem in the case of composite material, we have to deal with the estimation of the residual stress as well. So, and in that stage, at that stage it will be very useful that you have, means you are calculating the residual stress generation, and finally it will be implemented towards the commercial purpose application and all. Okay. So, these things I did, and whatever additive manufacturing oriented things I did, that I already demonstrated in the first slide, and these are the deposition, and you can also see here. See, this is the deposition that is going on within the material. So this is the single layer deposition is going on. On the basis of that, just I fabricated this one. Means several layer deposition I did make. So on the basis of this deposition, just within means after 42 seconds, it has been deposited. Thereafter this one, and finally, whatever was the aim, so I fabricated this one. Okay, and during my PhD, that I did this type of model development that is visible for you. See, this is the stress analysis for the simple plate only. This is for the simple plate, this is a cylindrical geometry, and this is the additive manufacturing deposited material over the composite by using the different scan strategy over here. So you can see over here. And by using these finite element tools, it is not important only you have to go for the simulation only. You do some part of experiment, you do some part of simulation, finally you can incorporate and you can analyze those things, interpret things within the research paper also, because nowadays it is very important to incorporate the simulated thing as well as experimental things. Both will be having the very significance right now. So that's why I did a lot of things on the basis of the additive manufacturing. See, for the different deposition I did. Different material deposition I did, deposition of the inconel for the on the inconel, deposition of inconel over the titanium alloy, and finally I have made some conclusions and some data. See how the molten pool varies from the 1 layer deposition to the 10th layer, and all those things I did during the postdoctoral research, and finally on the basis of that solidification behavior I calculated, and thereafter residual stress generation what is going on that I did for these things, and finally on the basis for the aerospace application I did I fabricated this structure. This one is the experimental one, and I did some extra advanced characterization of the material that on the basis of that I revealed those, and finally I incorporated simulation part, that is residual stress behavior of the deposited material, and finally I analyzed or interpreted those things, and I incorporated those things with the experiment, and then I made the conclusion on the basis of our analysis at IIT Bombay. This was the work actually integrated with the IIT Bangalore, so that I did. And we found out the region of the crack formation, means solidification, means what is the region of the solidification crack, and the residual stress was the predominant factor apart from the other elemental segregation and all. So that we have interpreted, and on the basis of that we have made the several publications as well. So these are the things. If you need anything else as a suggestion or questions is there, so just please let me know, that I will try to clarify from my end. Anything else if you have to discuss with me, like. Did you get something? Miss, कुछ तो पता चला होगा, है ना? I think. No, I'm not a master. Nobody is master over here. Just I'm also a kind of a student only. So just the things which I did and what I am going to plan and what I am doing, just I illustrated so that you would be able to get something at least, because you came from the some another paths. So we don't know actually what is going on there. So it may possible that I can get the suggestion from your side, so that I would be able to do these things, and you can also get some learning, so that you would be able to do these things, or your student will do these things in the future, near future now.
So very for somebody like me, is absolutely beginner. So this is
Thank you so much. And anything else if you want to ask, then please let me know. I'll try to verify those. Done?